smart manufacturing technologies. We are privileged to have him share his valuable insights on the emerging trends of intelligent monitoring, digital twins, and data driven engineering systems. On behalf of the organizers, faculty members, and my dear participants, I extend a warm welcome to Mr. Aiyappan Ramamoorthy and thank him for graciously accepting our invitation. Let us all join together in welcoming our distinguished speaker. Once again, I welcome you, sir.
Thank you. Thank you very much, sir.
So, over to Aiyappan, sir.
Okay. So first, my sincere thanks for you to invite me for this digital twin session, as well as for the participants, the faculty, for joining this session. So appreciate your time. So first, to look at this topic of digital twin. So we all have multiple views of what this is and why it is required, how it will be useful. So my objective of the session is at the end of the session, you should be able to explain what a digital twin is and also teach to the students that how this can be achieved and why it is important for the students specifically and why it is important for the industry. So that will be my objective. So with that as the objective, first, before I start my session in terms of, using the PowerPoint and the collateral, but I'd like to start with a question that what is the complexity that the digital twin is going to solve? There are a lot of things which are there, but let's take one scenario. Let's imagine that there is a line builder who's making a bottle filling line, right? As mechatronics engineering, there are businesses etc. which are in the business of implementing manufacturing lines. Let's take that as an example. And this is a bottle filling. Bottle filling could be for for shampoo or a cool drink or for various other consumer products. If you look at you're designing this machine and it's a conveyor as line. Now there are two aspects of it. One, how do you design it? And second is how do you commission it? And third is how are you going to operate it? Okay. So design. You are teaching the students in terms of how you are going to select the how you are going to do the design in terms of the fundamentals of engineering, what are the kind of conveyors, the motor, how the overall system is going to operate. And second is how the operations are going to be, how the production operations it is going to help and so on. But in between there is also a commissioning phase, which means from the design to the physical, it needs to get operated. So to do the operation, there are performance criteria, which means I need to produce 500 bottles an hour, right? And each of the bottle needs to be filled within 5 seconds. So there could be different criteria which will be there. Now, as a design, as a manufacturing organization, how are you going to determine that the system what you have designed is going to meet these performance criteria? And if these are not designed according to how it is going to perform, then there will be a lot of iterations, which means the filling, the speed of filling, what should be the size of the nozzle, the size of conveyor, the speed of the conveyor it is going to do. So there is huge amount of iterations which will happen during the commissioning phase. If that is not there, so you have a go live, then what happens is there is a failure, there is a correction. So always there is a problem when you go from the design into the production. The commissioning phase is going to be very critical. And the commissioning phase, if it is not tested properly, it is going to have serious repercussions in terms of making the system available into the market or into the production or making it live. So I hope I've explained this problem, and this is a problem which is faced by every organization, every manufacturing organization. And it is also important for all of you to understand because you are making the engineers who are going to make all these things. And the engineers need to understand that if this is not designed properly, it is not commissioned properly, then these issues are going to be there. And typical way of handling this issue is to run through multiple iterations. You do a tryout and the tryout will come with certain amount of feedback. Then you do some changes in the design, changes in the way the products are behaving. Maybe I add some, guides and filters and all that. Say if the part is moving, say if the bottle is moving, say this is the bottle, and if this bottle is moving on the conveyor. Now, what is the speed at which this conveyor can move? That also depends on the power and motor which you have designed. But if I move it really fast, then there is always a chance that this bottle is going to fall off, right? At what speed, and what is the shape of the bottle, what will be the weight of it, where is the center of gravity? Because if I move it too fast, then it is going to fall and the whole line is going to stop. Am I making sense? You can give the feedback. If there are responses, please, provide the responses because, it is much easier when you do a physical session. But if it is a virtual session, please use the response so that I'm able to understand that, this message is communicated or, if I need to change the way I explain things. Okay. So if that is possible, sir. So please, have the feedback coming in, maybe as a chat or maybe as a thumbs up or, whatever, the reactions that, the system allows.
Yes,
Okay.
sir. We can use the chat box, sir.
Okay. Thank you. Yeah, thanks. Thanks for the thumbs up. So the problem is there, and the problem is imminent for every system and every organization when they move from the design into the production. Okay. So now let me share the screen to explain that in this scenario, there are multiple scenarios which are there, but in this scenario, what a digital twin is going to do. Okay. So let me see if I'm able to share the screen. Yeah.
Yes, sir. It's visible.
Okay.
Now it's clear, sir.
All right. Okay. I'm also spacing this. Okay, so in this scenario, I mentioned about the bottling line. So you can see that this is a bottle filling line. And you can also see this is something which we have done, or one of our customers have done. You can see the company name, also so that this is not something which is fictitious, but this is a typical assembly line. They make perfumes in this conveyor line, I believe. And what happens is, it could be perfumes, it could be soft drinks, it could be shampoo bottles, it could be multiple things which are there. And if you can see this, there is the conveyor which is moving here. Here you have all the control systems, you have the pneumatic systems, the hydraulic systems which are there, and you have the control and automation systems which is controlling this. And there is also physics which is there involved because the conveyor is moving at a particular speed. So what you can see is the digital system. So you have a physical system also available. So in the digital system, you can see how the bottles move, and the bottles are filled. And once the bottle is filled, now it is going to be capped. So you can see that how you are planning for this whole system, and then you can also move for the whole complete line also. So once the bottle is moved across, how you can fill the line, and once you fill the line, how do you place the cap, and how do you play once you have this cap done, then how are you going to operate? How are you going to move the conveyor? Now, what typically happens is if you don't have the digital twin. So this is an example where the digital twin can play a very important role because the speed at which the conveyor needs to operate, the filling speed, the size of the nozzle, the liquid is going to pour. And if it pours faster, you need that CFD to understand that, there is no spilling. the speed at which, the time, what is the critical time that, it is required for filling this bottle. So a lot of complexities are there. And, when it goes, when we say the design is done and we go to the commissioning, and you see that there is huge amount of problems which comes across when you put this machine into shop floor. Now, what digital twin helps you is to create this line virtually, so that not just graphics, not just the movement, but the complete physics and the operations, the complete behavior of the real system is mimicked across, right? You are able to assess what kind of power and speed which will be required to operate this. Not only that, you're able to operate with that particular signals, that when a bottle moves and it is going to hit the other bottle, what is going to happen, what the speed of the liquid that it is going to flow through the nozzle, the size of the nozzle, every aspect of it needs to be completely understood as a system to ensure that the whole line is able to behave the way that it is designed to perform. Okay, so it could be done. In this case, it is a product. So the product need not be the product which the consumer uses. The product is also the machine that the organization sells it to their customers. So it is a B2B and a B2C. So here in this case, this machinery maker is a B2B maker. And as when you teach the engineers, it is also important that when you create the product design is also not the end product which goes into the consumer, which maybe here in this case, the shampoo bottle or the perfume, but also the product which are created by the machine manufacturers and machine builders, which goes into the B2B businesses. If you also look at it, the companies like ASML, possibly the only company which makes, machines for building the chips, is so complex in the world that, the whole world needs to completely depend on this one company based out of Netherlands for making the chips for the entire world. So this is becoming very important. And digital twin importance is to ensure that you are able to build and operate the machine that you are able to design, and this design is able to perform the way that you have designed for. So that's the first scenario in terms of why a digital twin becomes important. Now, as a business, there are the market is very complex. You have the industry which is going through various challenges in terms of cost pressures, the sustainability pressures, the market changing because of disruption in the market, as as in the case of EVs. It could be disruptions in terms of new business methods. So things which can come as a service, not just as selling as a product. So the disruptions are there, which are happening in the market in a big way. So how as an organization, the manufacturers or the industry is able to respond to these challenges faster, becoming more personalized and efficient. What is also becoming very important is also the products are becoming very smart. So what do you mean by smart products? Because already you are using a smartphone and smart TV and smart washing machine and so on. So when you say a smart, which means the system has intelligence, right? So when system has intelligence, which means it has a software which makes it intelligent, and the software has electronics inside, and this electronics needs to have powered by the electrical, which needs to have the mechanical system supporting each of this. So as a whole, you have the software, you have the electronics, you have the electrical, and you have the mechanical, and the whole system is is required if the product needs to be smart. Now, because the smart is the one which is required by the market, otherwise there's no competitiveness, it becomes extremely complex because of the multidiscipline complexity. How are you going to optimize? How are you going to connect all these pieces to ensure that it all works together? So earlier we saw the conveyor line. Now you can also see that it has every aspect of it, right? It has the even within the mechanical, you have the hydraulics, the pneumatics, the controls, a lot of things which are there working together. And as industries, you have these challenges, and the students whom you are training, they are going to face these challenges, and how well you're able to address all these challenges with the data, with the engineering knowledge, and also with the technology, which is going to help them together. So you have all these three pieces together. And when we bring this, let me move to the next slide. So you have two aspects of it in the digital twin. So in the digital twin, there is one is the physical side and another is the digital side. And both needs to work together. So it is not only you're working on the digital where you have the design and the behavior, but you have the physical side of it, how the digital design is operating in the real world in the shop floor. The connection between these two are really very, very important. And connecting both the real world and the digital world is the core of what you call as the digital twin. And if you look at the twin, there are a lot of twins which can be there. First, let me expand across on the two areas. One is the product twin and the production twin. So product. So what is a product? So earlier what we saw, a conveyor line, a machinery, that is also a product. What we typically use, it may be the chair, table, laptop, phone, car, aircraft, everything, all these are products. Now, what is then the production? So where these products are getting manufactured, you have it as the production. So as a digital twin, they need to have a combination of both the product and production needs to be there if you're going to have a digital twin in reality. Okay. So in the twin, you have three aspects of it. As you can see, first is design, second is realize, and third is optimize. Okay. So if you see this, how are you designing the product? It may be the water bottle that you're looking at. And there are designs which are there. It needs to, each of this has certain uh, uh, activity and performance that it is required. And the second is the realization. So realization means from the design, how do we take this design which is there in the digital, and how are you going into the physical side of it? One, in terms of how the performance of this bottle is going to be, how much load it can carry, can you do a drop, and whether it's going to break or whether it is going to sustain that drop load, or how do you take this into manufacturing? How are you, is it going to be in the aluminum or stainless steel or plastic? How well you're going to design these products, and the process of manufacturing it, whether it is a glass, injection molded, extruded. So variety of manufacturing which is there. What machines you're going to use, what operations you're going to use. All these aspects comes as a part of the realization. And third is the optimize. And here you have the physical job already there. It could be your machines which you have designed and commissioned, and the machines start producing whatever it is supposed to work. It may be the car, it may be the heavy machinery that you have done. Now, how do you bring back all these data and ensure that the design you are able to optimize it? There are two levels of optimization. One is what you're going to do in the future, and another is in the operations live as it is happening. How do you fine tune your operating parameters? And that is the optimize which comes inside. So there are three aspects in the twin. How do you design? How do you realize it? And how do you optimize it? Right? And this is one as you looked at it from a product perspective. And the same thing, you look at it from a production aspect of it. Right? So here everything. So what is the output of a design? Output of a design is, you have the bill of material and you have the drawings. The drawings can be in 3D, in 2D, or specifications which will be there, right? So you have a list of parts which needs to be manufactured, and you say that these are the material that you're going to use. These are the inspection that you are going to have so that the product can be uh, accepted into the production. So those levels you will be able to do that in the product. Okay. So we go into production. So what is production? So you have decided that this part is going to be manufactured. Let us take an example of a car manufacturer. So the design of the car is done, and I said the output of the design, which is the bill of material, a list of parts which are there, and the specifications in terms of drawings, 3D models, performance criteria, all that is there. Now, how this is handed over to the production? So you can hand over this whole thing into the production, but what are they going to do with it, right? So that is the production engineering which happens. So for making all these parts, you're going to make, there are parts which will be bought over, there will be parts which will be in-house manufactured, and you can look at it from the reverse. What are all the operations what are the parts which need to be manufactured in-house? And for doing those parts, what operations are required? For performing those operations, what tools, gauges, fixtures are required? How are you going to inspect? What should be the sequence of operations? So there is a lot of planning, engineering, and validation activity needs to be done before this product goes on to shop floor. So one thing we need to be very clear is there is a design, there is an engineering which happens, and there is also production engineering which happens to ensure that how these parts are going to be manufactured. Then you go one level down. So you have sheet metal parts. How are you going to do it? Stamping, the plastic parts, you're going to do it injection molded, how these parts are going to get assembled, if there are going to be machining operations which are there. So it needs to be painted. So a lot of these activities and operations which needs to be performed, and that is a lot of engineering which happens. And typically you can call it as a manufacturing planning, production engineering, variety of organizations calls in a different way. But point is, how do we take the design into the shop floor? And there you have the design aspect of it. So what is the output of a design? So, all these details will be designed in terms of what are the process steps which will be done, what activities will be performed in what station. All these aspects are designed and needs to be validated, which means I'm performing with a nut runner or a spanner or a screw, whatever it is. How do you select it? How do you ensure that these tools perform the way that you expect to perform? What should be the sequence? So told that we are going to manufacture a car. So you have to put a dashboard first or a seat first. Okay. How the sequence needs to be designed. How these, and these are complete engineering, and all these are as per what you're doing it in terms of production engineering and design. And the realization phase is where the commissioning happens. So this design, you're selecting the tools and fixtures and ensuring that the operation happens, and then you are doing the optimization phase. That is the production optimization from a production life cycle. So you have two twins, you have a product twin and you have a production twin. And in both aspects of it, you have it the design, realize, and optimize from production side of it also. And the other side, the two levels, what you also have is the digital and the physical side of it. Both has, you have components which you do in the virtual world, and how are you connecting with the physical world, in the real world. And once you are able to connect these pieces together, then you are able to say that the twin is in operation with design, realize, and optimize. Now, that is the core. Now, the twin does not stop with product and production. There are a lot of sub details into it. It could be a quality twin. It could be a human twin. It could be a logistics twin. The twins are enormous, but as a whole, it can fall between the product and the production, specifically from the engineering aspect of it. And what is how do you know that this is a twin, or what are the benefits of a twin? So you can listen very carefully here. So the twin and the AI comes hand in hand, which means the artificial intelligence can power the digital twin. So you have a digital twin which has the digital and physical coming together, and you are able to design, realize, and optimize as close as possible to the physical side of it, because it has both the geometry, you have the physics involved, you have the data, all that which is there. Now, bring the AI and AI concepts into the digital twin, then the power becomes enormous. So what happens is, with the AI powered digital twin, first thing is you are able to learn from the past. So with only a digital twin, what you can do is you can actually replay the past, right? That's one. But with the AI powered digital twin, you are able to learn from the past. So I hope you can take note of this. So you are able to learn from the past, and you are able to replay the past only with the digital twin. And second is, you are able to operate the present with the digital twin, but you are also able to optimize the present, which means as the systems are in the operation continuously, you are able to optimize whether the parameters you are optimizing, or criterias related to production sequencing, or the process parameters that you would like to optimize, various aspects of it, which we will see during the session. But you are able to operate the present, you are able to optimize the present. Okay. And third is you are able to predict the future. So three things you can do with the AI powered digital twin. You are able to learn from the past. You are able to replay the past, both. You are able to operate the present. You are able to optimize the present, and you are able to predict the future. So three things which are the benefit of the digital twin. So let me put that in a better graphics. As you can see, the top half is you have the digital, both the product and production, and the bottom half you have the physical of both the product and production. The product could be multiple, as you can see inside. It could be a consumer product, it could be a machinery, it could be a windmill or an aircraft or a car, whatever it is. So how well you are able to go through the digital side and the physical side. And the digital and the physical is also, in a way connected with what you call as the horizontal and vertical integration. So what do you mean by the horizontal integration? Is from the customer, you have the requirements to high level design, various concepts, detailed design, engineering design. You have the validation, testing, then the planning, you have the suppliers, production engineering, quality, inventory, logistics, production, execution, inspection, and delivery, logistics, customer experience, operations. So you have the complete side of it going through from the horizontal integration. And the vertical integration is where from the customer order, how are you delivering it across? So order from the CRM system moves into the production, maybe into the ERP system or the MRP system, where the orders are sent in, and these orders prioritized and sent into manufacturing execution system. And from the manufacturing execution going into the scheduling system, into the automation systems, and to the machines and operators in the shop floor. So you have both the horizontal and the vertical integrations. And how do we bring this across specific areas? There are process and process threads which are there available. Okay. So at this point, I would like to take a pause and get your feedback in terms of what the basic understanding of what the digital twin is, why it is required, and how it is practical in the shop floor. So give me some feedback. If you have some questions, please stop me here, because then we can go into a lot more of the how side of it. As of now, is there anything that you have questions, you have some feedback? Please let me know.
Yeah, we request the participants to unmute yourself and talk to the resource person. Or you can use the chat box also to post your feedbacks or clarifications to any, so that it will be looked into. Thank you, dear participants.
Okay. So I have one question from Mr. Prabhakaran. Is there separate workflow required for the digital twin? And from others, I don't have any questions. Please, I'm able to watch the chat window. So if you have questions, please put on the chat window, or you can ask, as Prabhakaran sir mentioned. And if there is doubts, please ask me, uh, immediately, or at any point we can stop and discuss this. So, Prabhakaran sir, I'll bring that into. There is a separate workflow required for the digital twin, because the subject itself is very large, and the most important aspects of it is, how do we create a digital twin? So you can actually create a digital twin for the light and the fan, or for a complex machinery, or it could be a boiler, and it could be a turbine, whatever. Important aspect of it is, uh, I mean, what is the problem we are going to solve, and that will drive the workflow also. And in certain cases, you also use a reduced order model or ROM model to do that. So we can get into the details, whether it is single physics, multi-physics, and what is the cost of the problem that you're going to solve with the digital twin. So those will drive the workflows, but we can discuss. If we have specific questions, we can discuss. But some of the areas we are going to go through in the subsequent slides. So another question from Dr. Bala Narasimha is: Are we using any software to create the digital twin? Absolutely. So there are softwares which are there. I come from Siemens, so obviously there will be a bias towards Siemens. Sorry for that, but there are softwares which are there. Again, the softwares are multiple in nature, and it needs to solve certain problems. So, which means there is a combination. So, we also have what we call as a digital twin composer. But point is, the digital twin, the software to operate is depending on what the problem you're going to solve. So, you will have model-based system engineering software, or as typically what you call as a 1D software for the concepts. ROM kind of softwares, you will have the simulation softwares, CAD, the validation, and the softwares related to the physical testing. So how do you connect with the sensors and bring the data specifically from the product engineering, maybe for the NVH and leakage, various other performance criteria. You also have mechatronics based software which can do multiphysics. It can also take in the gravity, and be able to perform automation with PLCs and systems together, and then capturing data from the real world with sensors, instrumentation, IoT, SCADA, a lot of things, and various information coming in from the machines side. And it needs a combination, because what problem you're going to solve will drive what the software is. For example, if you say uh, there's a small and SMB, small and medium enterprise business, which are there, maybe in the near Salem. Let's take an example. And the problem is the not able to meet the delivery times. Not you have a lot of orders, and orders from all across India and the export market, and there are variety of batches and products that it needs to be delivered, and you have a capacity, which there are resources which are there are people who are available. How do you ensure that, with all the orders in place, what should be the order that I'm going to do today, right now, to ensure that all my orders are met? Or if I'm not going to meet, then how do I prioritize? What should be the sequence? So this problem is again a digital twin problem, and it also needs feedback from the shop floor, from the field, because suppose say maybe there are few people who are not available. There is a vacation. There is there is a machine which is down. So how do you continuously make these changes to ensure that your objective of meeting the delivery times are are met? Okay, so you have a system which could be a scheduling system, again a software, but how do you operate the physical side of it, taking in the orders, what exactly is happening on an hourly basis, shift wise, you get this feedback to ensure that there is a closed loop sequence the system is able to generate. Again, a digital twin, but in this case, the digital twin is creating the schedule. And what it delivers is immensely powerful, because you have a system which you are able to promise to their customers. It may be SME, but able to give it to the customers that what time the order will be delivered, right? At least out of the shop floor. Now you can also take it across through the logistics. That's the second side of it, with telemetry, and you have the simulation going. So digital twin is applicable across. Maybe I'm also answering another question: is digital twin, who are the industries who can use the digital twin? Can be everyone, because this needs to be done. There is value for everyone, but you need to understand what is the cost of not doing it, to ensure that you're able to build that twin, which is bringing in a significant amount of business, which can actually ensures that its returns are much higher than the cost involved in doing it. Okay, some of the so that is on the software. Yes, great session. Could you please tell me some of the student levels nerds in interdisciplinary project ideas? Plenty. So we can discuss. In fact, what I told is scheduling twin. If you're scheduling and sequencing twin is again is something which is applicable for every industry, every customer, small and big, because the order needs to be produced and provided to their customers, irrespective. It could be a 10 crore company or a 1,000 crore company. This problem is there, and the twin can actually help them solve the problem, minimize the inventory, ensures that the material, based on the current material availability and the people available, you are able to produce it. So ideas are plenty. We can have a discussion on that, or I can put it across. You can message me. We can discuss on these ideas. Sure. Can we make our lab experiment using the digital twin? Absolutely. So this is something which you can do that, and that's the advantage of the digital twin. So you can create the digital model, and for the physics for the physical data, if you have the data, you can do that. Say, for example, like it is an operation of a motor, for example. So you have this data, you can do. Otherwise, you have the software, you can create a synthetic data and create variations of it, and you can actually operate the digital twin. So you have both these scenarios working together. Absolutely possible. And in fact, you should do experiments, and you can also bring these experiments with the problems which are there in the neighboring industry. Say, for example, there is a quality related problem. Maybe there is an auto supplier, quality related problems in terms of how well there is a high level of rejection, or the rejection goes beyond 1 or 2%. So the costs are very high, right? So where is the source of the problem? So now you need to create a digital twin of quality. Then what is and that is the most important aspect. So it is an issue with the product, or it is an issue with the process. Okay, or is an exception. So exceptions, you have to keep it aside. So if it is related to the process, then how do you create a twin of the process to ensure that can we create a twin of the process, and do the experimentation digitally, right? If it is the product related, they obviously, you can do that from a product related. So we can do that, and you can do that in the lab experiments as well. And if you want some thoughts and projects, I can provide. But even much easier is um, you ask the industries which are there nearby. It could be chemical, it could be process industry, it could be making textiles, making leather goods, whatever it is. Like, it could be any kind of industry. uh, get these problems across. The problems are very important for the digital twin because they cannot be theoretical. We need to ensure that if we are creating a twin, it needs to solve certain problem. Okay, how to solve it is where the knowledge is, and that is where you will come pretty big. And you see that the technology is there. So these are the technology. This is the business problem which is there. Now you create a prototype how to solve this problem, and this problem you got students can actually solve it for the industry which are nearby. So is it open source or licensed? Both. There are softwares which are open source. There are software which are licensed. Most of the softwares are available, even if it is licensed. For the students, it is mostly it is all available. For a student edition, all these are free. People can download and use the software. Is this digital twin help in predictive maintenance of a rotary machine? Yes. So this is definitely there. We'll have some examples also of the digital twin. Now, this use case, for example, coming from Mr. Virendra Singh Thakur. So this is becoming very popular. And, for example, from our side, there is a twin which you can actually download and straight away use it, because this is something, which is a repetitive, and there is a lot of people looking for it. So there are these twins are productized, right? So you want to create it, or you want to do a similar one. Definitely these are available. I will also go through some of these examples. If you need more, just put this across on the chat window. I will provide what is there coming in from us. But you can create these systems as well, because you have the IoT systems which are available, and you can bring this data. The learning happens, and there are productize which are available, and you're able to build your own systems as well. Okay, all right. Now let me move. Thanks for all your questions. Really appreciate. Otherwise becomes very monologue, and appreciate all your questions. So digital twin, we saw, is a virtual representation of a physical object. Again, the object is dynamic; it continuously evolves, so it is able to mimic and mimic the behavior, not just the graphics. Right? It is able to behavior. It able to mimic the performance, and able to continuously evolve with the life cycle. Okay. So as we also saw, there are three stages broadly. We look at the twin. So you have it at the design stage, you have it at the manufacturing stage, and you have it at the operations phase. Operations includes maintenance as well. So first is a precise virtual representation of a product or a process. And whatever level that we do the twin, there is always a difference. Twin is always a twin. Twin is not equal to the physical. Okay. The challenge is how close we are to the physical, physical world is the digital twin. Now, you also need to understand that how close it is required. Because if we are able to solve the problem, that is more important than getting really theoretical that how well is the twin. Because in any aspect of it, we need not do the twin in its entirety, right? If I'm going to solve a problem related to quality or a production or performance, I can put a boundary and focus on those areas, because by having this twin, that is what my uh, benefit I'm going to have by having this twin. So if the twin is not going to solve any problem, then there's no point in having the twin, right? As I told you, I can have a twin of my fan also, but you look at the fan, by having this twin, what problem it is going to solve, right? In a year, maybe there is a failure, or even it may not be a failure as well. And even there is a failure, I can get it repaired. The downtime is not going to cost much, and the replacement cost is also not very high, and the criticality is also not there. Then the reason for me doing a twin of the of the fan possibly is very limited. But then imagine that the scenario is of a boiler in a power generation. So, or a turbine, or it could be anything which is mission critical. And these systems, if they are down, then the cost of downtime is enormous. And that is where the benefit comes, where if there is the cost of failure is very high, or the frequency of downtime is very high, and that disrupts the production, then it becomes very important that you create this twin and also solves those problems. So you're able to predict those failures in advance to avoid those failures, or if failure happens, what best you are able to do it for alternate. Now, this twin is able to simulate, predict, and optimize both the product and the production system, as we saw earlier, and it has multiple representations. So to model different aspects of the physical behavior. So when you say multiple representations, obviously it has the physical world as extremely complex, and we need to ensure that what we are going to mimic or what we are going to create as a twin, not every twin, every aspect needs to be done, because there is always a cost associated to it, which means cost means time, and then the complexity. And if it is not going to help in solving the problem, maybe those things may not be required. And that is the decision point, or that's the understanding and maturity which needs to be there. And closed loop digital twin. So digital twin need not just be the digital, or a lot of people also come with an understanding that, okay, I have my motor running, or I have my plant running, and connect all the sensors and into the cloud or into an automation system or a historian, and I create analytics out of it. Then is it a twin? So so it is the starting point. It definitely is not the twin, because you don't have any digital system representing and how well you're going to optimize it. Even if you are able to do with the data, so you can go to the level of at least a data twin. Okay. So the data twin, once you have the information coming in at the frequency, and once the failures are there, then you can create the ML models to ensure that this twin is able to predict failures and so on. But what is also important is how well you are going to use this data to optimize your process parameters, right? Then the data needs to actually feed into the physics model. So this physics model is helps to operate the not operate, optimize the process parameters, so that your product is optimized. So how these multiple representations are interrelated? Very good question. So from Mr. Dhanapal. So here in this case, for example, here I'm taking an example uh, of a mixer. So the mixer will be there initially, in this case, could be a chemical, it could be a tire manufacturing, it could be, variety of operations that we do. So in this mixer, blender, whatever be the scenario, now in the mix, there are multiple raw materials which are brought inside the mixer, and in the the drum is rotating at a particular RPM. It may be heated. It could be the material could be operated at particular recipe that it moves on the operation. But what happens in a real world is the input raw material coming into the mixer, into the drum, also varies. Now, what is the level of performance? For the level of performance, you need a high level of consistency to give the level of quality. Now, since these parameters are varying, how do you optimize these parameters? And that is where the multiple representations are interrelated. So you need the feedback from the physical system, and then you need to have the digital twin of the physical system to ensure that how the mixing is going to happen. If the granule size are varying, if the raw material physical properties are varying, how will this product, I need to have my product to be consistent, right? And that is where these twin becomes very important. Let's take an example, which is of a product and production. So on the digital side, here I'm taking an example of automotive manufacturing, which is simple to understand. So you have the requirements. Requirements can be performance criteria, could be sustainability, it could be a cost, a variety of inputs. And as the intelligent systems are there, you have a combination of mechanical, electrical, electronics, and software. You have the product validation of the car vehicle, how the product is going to perform. Process validation, so how the product is going to get manufactured and how will you validate these process, and then goes into the operation as built and as serviced. Now you look at the physical world, and in the physical world you see that the customer feedback input, what is good, what is not so good, and you have the R&D side. So you have testing. The testing could be for the internal testing or the NVH testing. So a lot of testing which happens, and then the prototype for engine performance, HVAC, entertainment, NVH. It could be for crash, multiple sites from the product. Could also be for commissioning. So as I mentioned, during the start of the session, you also had the problem was commissioning problem. So there the problem was the bottling line commissioning. Here in this case, the assembly line commissioning, welding line commissioning, because imagine that you're going to introduce a part and introduce a product and the commissioning, which means you have all these spots which are there, right? Weld spots which needs to be done. And if you are starting to wait for the physical part to be there and create a prototype and teach the robot and create the program, the PLC, it's going to take a lot of time. So how well you are going to do that digitally? And again, how are you going to do first time right? Otherwise, the launch and the delays are going to be very expensive because the production line cannot stop for introducing the new product. So again, there's a big problem. You will have a window of Saturday, Sunday, or maybe some time off which will be there. Then you have the production and the service reporting. So if you look at this, you have the digital world and the physical world, of the product. So in this case, a car, how well the digital is getting connected. So the digital is connected largely through what we call as the PLM system. And the physical world, you have the OT system. So you bring these two things as, here I have represented as a product, but just think that these are the IT systems and the OT systems, and the merger between the IT and OT. You have the twin needs to bring all these two aspects together. Okay. So, and that's also again, you have the close to digital twin. Otherwise, these individual digital twin also can become silo, and it will be of a suboptimal performance. Okay. So it could be a car or it could be a dump truck. So the dump truck also getting extremely smart these days. So there are electrification coming on the dump truck. You have AI, the sensors and connectivity, cloud computing, everything coming across all these things together. So let's look at one level deeper what this twin mean. We saw a lot of these concepts, but in a real world, when you're doing the design, how do you do this? So here is an example. Here, this is again a machine. So this machine, is an inspection machine in the bottle filling. Could be an inspection, could be bottle filling also. So in this case, what you see across here is there are mechanical things which are there, like a limit switch, that at what point the bottle needs to stop. And there is a relay. So there is a cutoff, and you have an interface which is there, a HMI, and that the operator can use and touch. And there's a cabinet with a lot of electricals which are there, IOs, which actually brings the sensors into the machine. There are limits, safety limits which are there, and the product limits is the hose pipe. There is There are PLC automation programs which are there, pneumatic components which are there, air and valve units. So a lot of things which are there when you are designing the system. And we are designing the system. You can also see that you do in CAD platform, which you are pretty familiar with. And as you do the design, then you also create your electrical designs as well. So how the signals are going to be, what should be the speed at which the response are, you're going to get. And to use this electrical design, then you also take it into your PLC program. So what you are also seeing is the ladder logic, which gets created. Now, once you are able to bring these pieces together, you have the electrical system, the automation system, and the mechanical systems together. Now, what you're able to do is you can actually use this to commission. And here in this case, this commissioning is virtually. So we'll also take another example, but from the design standpoint, how you are able to drive the design into manufacturing, into commissioning, and you have a first time right kind of scenario because you have a twin which is able to represent the physical world. Here in this case, it is a new design and there is no physical available, right? So in this case, the physical, while in terms of reality, it is not there, but it is able to mimic the reality because the systems which are going to operate the real twin are the ones which are going to operate the digital twin also. Okay. So how do you create a twin of the reality? Here, in just an example, it could be the data. There is no digital available, for example, and I want to scan this information, and maybe there is an imported part. I want to do a reverse engineering and bring this scenario. So I have a scanner today. These scanners are pretty much simple, available. Most of you in the colleges, you would have laser scans or white light scans, which are there, the products which are failed, there are breakages which are there. Now, these scans gives pretty very close representation of the physical. But the moment, the moment you have it on the digital world, there is a lot of things which you can do. You can add material, you can paste material or weld material depending on the type of geometry what you have, and then make some changes or do some repair, depending on what kind of activity which needs to be performed on this mission critical component. It could be that, or it could be a scenario which is from a medical side of it also. So here in this case, imagine that I really have a problem. I have a ligament tear, and I need a knee replacement. And this knee replacement is very personal, depending on how bad my tear is, or the condition that I have between in my knee. So I take a input. The input can come from a MRI, right? So the MRI data, I can bring this inside. The moment I have the MRI data, then I can start designing. It could be for dental, it could be for cranial implant or a knee implant. Now, how I can actually create my implant and this process, this is a generic. I can keep a generic design and say this is how it needs to be. But then what happens is, depending on the wear and tear of the individual knee or the muscle, the inner form gets created, which means, like, with a big block, I cut it off. Now I know that this is the actual one which I'm able to provided for my patient. So in this case, you're able to do that. And this preciseness is very important because that determines what the success and the failure of the implant. Because if there are variations, then there is going to be more pain for the patient who is going to have this implant. More precise you are able to do, more precise that the location and the placements which you are able to do that digitally. Now the physical world, and in this case the patients, they are able to get their rehabilitation much faster, the way that what is expected. Okay, so not just on engineering, but from the pharma and medical device side of it also, or implant side also. So let's move on into the design where it could be variety of designs. It could involve physical motion, which could be there, engineering design, optimization, which could be there, and it also can be a systems level engineering, so multiple levels. And now here in this case, you're able to operate this twin. So now you can see that these model in loop, hardware in loop, software in loop scenario. So these are things which you will be able to do that very well inside the colleges. So there was earlier a question that how do we create these experiments or digital twin in lab. So digital twins in lab, very much possible, because all your models are there digitally. What you have will be the physical way how you interact with the model. This is one example. I will also show maybe another two more examples of how do you build this digital twin. So digital twin with here in this case, in operator, how the motion happens, and how do you are able to do the control, but operate the digital landing gear. But the motions and controls, everything which is there, all these are physical, which is possibly easy to build. But what is really complex and expensive is the digital, or the digital side, which is actually like representing the physical side of it. So these are options that you are able to do that. This is something which is important, electrical and electronics system development, because we understand mechanics pretty well and we understand the electronics pretty well. But what happens in between is the electrical piece, how well you're able to connect these wires together, how do you do the networks, the input output, the signals, the speed of the signal. So how well you're able to have this cable harness, and the response of these harness determines the success and the failure. Imagine that you have an autonomous vehicle or a car, and there is a sensor. Maybe it is a camera or a sensor which is there, and that needs to provide to the ECU, or it needs to connect to the onboard computer. And that computer needs to set it to the main computer, and then operate the brake, and then perform the brake. So there is always a time lag which happens, and how well the electrical systems need to be connected. The response time which are there plays a very important role in ensuring whether there is success or failure. Could be for aerospace, could be for automotive, but any complex systems, as you can see, the wiring becomes extremely important, and plays a critical role in ensuring these intelligent systems are working the way that you're designing to perform. So twin not just involves one dimension, twin involves so many dimensions, and uh, to ensure that you have a holistic digital twin. And the next side is the electronics side of it. So how well you're able to, you have a lot of applications here, like, you have the PCB layout design, and you have a chip design. From our side, we have the pads and expedition, and how well you're able to connect these pieces together. And, again, a big example of the digital twin is also the autonomous vehicle. So autonomous vehicle, it has to operate in real time, right? So it needs to understand what climate conditions are, what the environment is, whether it is day, night, sunlight, rain, maybe floods which are there, or a heavy wind scenario. Needs to understand all these aspects, and also determine at a speed that whether the person crossing is, if you look at it, the person crossing is a child or a dog, or or a stone. So we don't realize it, because for us it happens intuitively. What you do in your when there is a small stone which is there, or a human which is crossing, so all these are going to have a huge impact and the twin needs to be trained. And this training can be on only the synthetic data, because the level and the maturity to do that, it needs to run maybe 10,000 kilometers, 20,000 kilometers. It needs to run to actually learn to ensure that it is able to operate on the physical world, and that the twin actually helps you to operate your product, here in this case a car, on the digital world, and get trained. So if you look at it, like 400 prototypes and across like 100 years of today, it needs to physically operate if it really has to learn. So very impractical. But then the twin becomes extremely helpful in performing these kind of things, into the reality. So we looked at a lot more on the product side. We can look at it from the manufacturing side, the production side of it. So production. So what is the manufacturing today? Mostly, you have assets which are fixed assets, which means you have machines, you have robots, you have fixtures and toolings which are there, specific dedicated tooling. There are automation which are there. So there is with the automation. So when you say, people say that the industry 4.0 and automation. So if you look at it, this is a double-edged sword. And when you have everything completely automated, is it something? Is it optimized? Then you have the question that if it is completely automated, now the product changes. Say this product is designed for, say, motor manufacturing plant, and the size, shape, and the type of motor is changed. Then what happens to this plant? Okay, so it becomes very complex when you have completely automated everything. The moment the design changes, how well this new plant is going to accept this design. So are you going to create another plant for performing this, or make changes on the existing plant with a level of automation? So those are the questions which needs to be understood before going in for a complete level of automation. So at this time, just wanted to take a break to get any questions from the product side of it before we go into the manufacturing side. If you have questions, if as of now things are okay, just give me thumbs up. Otherwise, have some questions, please.
Dear participants, do you have any questions? Kindly unmute and ask the question. Otherwise, you can use the chat box.
Okay, so there are no questions. Are we progressing? How well the product when we are able to understand? Is that clear?
Yes, sir. It's clear.
Okay, thank you. So I'll go to the manufacturing side. This is the typical manufacturing. But what is the future of manufacturing? So the issue with the product manufacturing, or the high level of conventional manufacturing, I would say, is line disruptions. The second most important thing is lack of flexibility and resilience. What it means is, I've created, say, if it is going to be only one type of product and the product are not going to change, then things are relatively simple, which means, say, power generation. The power plant hardly changes after it is commissioned, right? Typically, you can improve the performance, but do predictive maintenance and so on. But the product is not, the output is not changing. Same thing maybe for a refinery and so on. So if there are products which are there, which are pretty much constant, which are not going to change, then there is at that level it is relatively simple, because you need to more focus on the optimization, operations, and maintenance. But if the products are changing, say a high level of change and variance which are there, maybe there is chemicals, pharma, automotive, electronics, mobile phones, like, if you look at any other side of it, the products are changing at an unimaginable phase, and each of this change is going to cause disruption in the production. And having this digital twin is very critical to avoid or minimize the production disruptions, and to look at flexibility. So how well the existing, say there is a new model of a tractor which needs to be introduced on an existing line, right? Because for every new product, you cannot create a new line or a production. So it needs to go into the existing line. So what happens? So I'm using a fixture. I use the same fixture and make the use it for this new model, which is possibly having a little change or different size of casting which is coming in, or I need to create a new fixture. So what is the cost of doing it? The problem is not only a cost, you will also have a setup change. So if a product A comes, I need to use this, product B comes, I need to do this, which means, for every product, if a product A and B comes alternatively, I cannot keep changing. Then I need to make a batch. So there are costs for every aspects of it. So this flexibility is very critical. So how well you're able to ensure speed and delivery of these products? It's not only enough to create a product and deliver the product, but are we delivering the products according to the schedule that the customer wants? They can't continuously say, I will give only yellow color cars first, and then I will produce black color and then blue color products. Assembly line is going to have products with multiple colors, with variants, what the customer wants, right? And the sustainability becomes extremely high. There are compliance, and there is more government and legal which is there to ensure that how well the organization is going towards the net zero, right? So both in terms of their end products they manufacture and the production, how well they are able to ensure that the whole manufacturing and the organization is able to meet their sustainability targets. And these days we see a lot of issues related to cyber attacks and the problems related to growing skill gap, lack of talent. And that's something which here with this, faculty development program, we are clearly able to address some portion of it. So how well you're able to address this, in the future design and engineers, but also looked at, how well you're able to avoid these issues, from a manufacturing organization perspective. So if you look at what is that technologies which are there, a lot of things which are changing. So one is the physics-based simulation and data. So this is becoming, so data, the moment we have a lot of data, what you're going to do with this data, how this data is going to fuel this twin, right? So you have a physics-based information. Say, for example, if it is, let's take the same example of a motor. So the motor as a physics, we can have a complete representation of the motor. But what you also have is the data which the real motor generates, and you're able to match these performance, able to find out remaining useful life, how do you optimize a lot of things which comes when you have a physics based simulation, when you're able to create a synthetic data, when you're able to create a real data, and these data comes in from the IoT and sensors which are there. You also saw the scanning, how the scanning, we are able to use it for remastering. And then, you have the cyber physical systems, where the systems, the physical and the digital systems working together. You have the machine learning and AI coming in. So a lot of areas. Say, for example, the simplest one is the inspection. As I said, one is the predictive maintenance is becoming more productized. Failure prediction of rotary machines becoming extremely popular. A lot of people started using it. So it become productized, which means you can download and use it. AI for visual inspection. So you have a camera is able to identify any anomaly which is there from the physical world. If there are parts which are missing, the parts which are not aligned, addition of parts, comparing what design with what parts, all these are something which are available and gives an immediate benefit or a high level of benefit for the manufacturers. For example, the project could be based on the order, what kind of delivery, and you are able to train the visual inspection for the camera to look at how the product are going to be. is something like, can be implemented very fast, be it a large or a small organization. It could be, label printing into the bottle. At what level height needs to be printed? What is legible? Is there any scratch? Is there a twist on an angle which is there? So these are all scenarios which which the AI and machine learning could be used very well in quality. Again, a lot of engagements which are going on in the AR and VR, typically where you don't have a physical access to these assets. Because, for example, again, the typical use case is the windmill, where the maintenance operations are there, the windmills are there in remote places, sometimes in the deep sea. So how well you are able to leverage the expert who is there in maybe in a different city, in different country, to perform certain maintenance operations, or perform certain, say, part replacement, or ensuring that these systems are up. And the technology plays a huge role, because you're able to virtually have the expert, as good as he is, physically available to solve this problem. So, working together, both the persons wearing the same AR device. So the person who is there in a different city, in a different country, and the person who is just next to the, here in this case, a windmill, both see the same environment, are able to mark up, perform the activity, and able to ensure that these systems are up. These are also coming in the medical field as well. Okay, additive manufacturing, advanced robotics. So all these are areas where there is a technology which are bringing into the manufacturing side. Now the question for us is where to use what. It is not just because I have these things and it needs to be used across into the shop floor, but what is the cost avoidance, or what is the benefit that I'm going to have if I'm going to use this. And finally, it needs to measure in terms of returns. Because if I'm going for flexibility, so how well I'm, probably today I'm introducing a product every year. Now with a flexible manufacturing, because to make the die change and create the fixtures and tooling itself takes 6-7 months. So I cannot, with my current process, I'm not able to introduce anything less than a year. Let's take that as a constraint. Now, with the flexible manufacturing, so with the flexible manufacturing, with a different kind of a manufacturing process than, say, in this case, the products are welded not in a conveyorized line, but there are multiple robots which are actually, like, held in different stations. The robots move and, fix all these well points or whatever it needs to perform. And there are certain parts which requires stamping, are produced by different mechanism. Maybe that is produced by additive manufacturing. So which means you are able to avoid certain die making process itself, if you are going for advanced level of manufacturing. But again, understand level, what technology needs to be used, and what is the benefit in terms of real returns that I'm going to have, or a competitive advantage that I'm going to have for adopting certain technology. So scanning related, AR related work instructions, so machine to machine collaboration, a lot of things which are there. And important aspect of it is, before doing anything physical, can we create that digital twin? So if we say these are things which I'm going to introduce on the shop floor, rather than going directly there, can I operate my plant digitally and see that what benefits which I envisage I'm able to achieve it or not? Okay. Let's take, for example, if I'm going to have these technologies implemented, I'm expecting certain level of benefits, say in terms of productivity. I'll be able to produce so many new vehicles. Can I create that in digital and operate or run this plant digitally to identify and confirm or validate that I'm able to achieve the objectives that I looked for? So before making any physical investment. And that is where academic institutions can bring in a huge role, because any industry which is looking for, like, clusters which are doing what kind of capacity they are building, can actually do the consulting to ensure that whether these capacity can be met or are there alternate methods to do it. And the production simulation, the discrete event simulation is really very, very critical for manufacturing organizations to create the production digital twin. Okay. It could be an assembly line. It could be manufacturers who are doing the stamping products for household goods or white goods. It could be any kind of manufacturing. But as academic and students, you can give projects to create the digital twin of the production, which means your digital twin can mimic the real world production. So you can operate the plant and see that how much products you are able to manufacture on a daily basis in a shift or whatever with the kind of machines and operators who are there available. The moment you have the digital and physical matching each other and you are able to calibrate, then you can look at optimization. And that brings a huge benefit for the manufacturers. It could be small, medium, large, but then, because with the same level of investment in capacity, they're able to produce more or, reduce the cost of manufacturing operations. So if you look at the manufacturing, so how was it maybe 100 years back? More fixed and manual. So, we moved towards increasing the, we actually moved on the right hand side where we brought in a high level of automation. So it is for a particular product, we're able to manufacture at a really rapid speed. But then the problem came in, when the products started changing. Then we have to go back to more flexible and manual. Here is where more of engineered order products, defense and aerospace related products went into this direction. Automotive, consumer goods, electronics went into the fixed and automated direction. And now what is emerging is more flexible and autonomous production. So how well you can help the organizations become more into the flexible side and into the autonomous side. We also saw, I gave an example of scheduling sequencing. So how well the system can itself identify that what is the product which needs to get produced as a next sequence. That is autonomous sequencing. That's also a very critical part of Industry 4.2. If you want to, that could be one project or multiple projects as faculty you can provide to students, because as a whole that can boost the productivity of the industries which are there in the country today. Okay. So what is the manufacturing process digital twin? So earlier we talked about the design. The output of the design is the bill of material and the drawings in 3D and 2D. And the manufacturing planning is where the engineering bill of material is transformed into manufacturing bill of material. The core portion of it is you do a make or buy, right? What you're going to make in-house, what you're going to buy and assemble it, right? And do the process planning. What do you mean by process planning? You define the process which needs to be performed for making the parts to ensure that the output is created as a product. So that is the process planning. So sequence of operations, what operations are required, tools are required, fixtures are required, so on and so forth. So those are the process planning and validation of these process. So if I'm going to say that, this is the sequence, whether in reality I'm able to perform this. Is this current fixture what I have is able to use, is able to adopt for the new product or new change which is coming there for the change in the casting design. So is that I can validate it digitally. I can also commission it. We saw the virtual commissioning. We'll see that briefly. And also how well I can improve quality. Can I simulate the quality? Can I digitally run my production and say that, okay, if I'm producing 100,000, how many parts will pass, how many parts will fail, so there are Monte Carlo simulations and simulations which are there to predict based on statistics, right? So again, taking an example of automotive manufacturing. So automotive, you have the sheet metal parts which are pressed in the body shop and press shop. So started created in the press shop, which goes to the body shop for welding, and the welded body goes into paint, and the paint goes into assembly. And it is also fed by engines. That is the powertrain shop, which actually does the machining operation and gives it to the assembly. So if you look at, I'm showing an example of a press shop. Okay. So how well you are able to create a twin of the press shop? As you can see, these are really very high-speed machines. In 1 minute, there'll be about 10 to 12 panels comes out every minute. Now, a productivity improvement of 5-10% actually brings in a huge amount of benefit to the organization. Could be a press shop. We talked about certain tires also. So there are curing presses which are there. For a curing, it takes 5 minutes to cure, and because of that, tire manufacturers have about 200-300 curing presses. Now, if you are able to reduce the cycle time from 5 minutes to, say, you shave off 10 to 15 seconds, it's huge, because the volume is so high that if you calculate it for a year, you compound it for 10 to 15 seconds for one tire, and it takes whatever, like in 1 hour it produces about 10 tires, and then you calculate it for 24 hours and for 200 machines, and that is for one day, and you just multiply by 350 days. Just see that, there are crores of money which could be saved, if you're able to create the digital twin which can optimize the performance. How you can do that? So it could be for the rotary machine. You're bringing the data going through the edge, and this data collects information about the process, the machine, and the product, and the AI looks at how well you can improve the parameters, and that is where the optimizing the present happens. So you have the data, so you're able to replay the past, and you're able to create with the simulation data, you're able to predict, but you're able to optimize the present when you're able to have this twin. The same level of optimization could be from a sustainability aspect also. So you can actually operate the plant digitally, and with the boilerplate information related to energy consumption, you can digitally run the plant to identify. Here in this case, it's like, you run the whole plant and identify how much is the energy consumed by various machines, and create a Pareto in terms of what are the top consumers of the energy. And you can use the simulation, here in this case, discrete event simulation, production simulation, to optimize for energy consumption. It could be for optimizing the inventory. It could be optimized for delivery, optimized for productivity. It could be various aspects, but you could also do it for energy consumption. And you can also specify marks. All these are important, but then I can have weightage for assigned for each of this. Now, again, virtual commissioning. So example, what you could do it in the lab, in the shop floor with a digital twin. So in this case, as you see, there is no physical factory here, right? There are only operator, and this operator has a control panel. Here, he has a physical control panel. Here, in this case, it is a hardware in loop. But this hardware panel also is not required, because you can have a digital panel also. So you can completely do the twin sitting in your college, in your labs, to create a production system which you can do the design, you can do the line design, create these conveyors and CNC machines and all that, and also create PLC programs. And the PLC programs, the ladder logic controlling the production, to look at how well the conveyors behave, the passing through the signals, getting the information. So, so that the robot can come, pick and place, and here maybe there is a machining happens. And, there is a cycle time which it takes, and use the same machine, save the same robot to place for the second machine as well. Now, this is the reality of what is happening on the shop floor. Now, with the digital twin, what you can do is, you can actually operate it as close as possible. Now you can see the simulation panel. So you can see all the signals, how the behavior is. and then you can connect with the automation, and it is also interdisciplinary, right? So the electrical engineering students, in your college can participate and they can create the automation program. Mechanical engineering students can design and create this layout. The automation or electrical engineering along with mechanical engineering can create the programs for the SCADA or the PLC. The robot programs could be created. Robot programs for the movement of the robot could be simulated. So the whole system can be done as a twin inside the college. Could be used for training and project creation as well. And if you're able to show it to your local manufacturing organizations, you can actually do consulting and projects which you can solve real world problems as well. And to bring the digital twin, you can use the scan. The reason why I am displaying this is, you don't need to, you can create a digital of the factory to create a representation, but you can use you can use your photographs, your phones to actually take multiple angle of photos, and there are software which are there which actually can take these photos and create the cloud model. Okay, so then what happens is you can do a white light or a scanner, laser scanner, but you can also use pictures to create the models, so you have a digital representation of the factory available, and you can make the changes. So assume that I'm there in this room and I want a nice picture to be here. I just take three, four photographs. I have a digital representation of this room. I don't call it as a twin, but just a representation of the room. And then this is a scan data. And then I have a digital photo frame, and I place this across at what level, and then start changing my design. So the usage is enormous. It could be for a paint line as well. So earlier we saw the stamping line. So here in this case, these are all very, very important use cases. What you are seeing is not just the graphics, but so you see the body going into the dip tank and do a complete rotation and bring it back, right? Now, how will the liquid goes inside? Liquid has gone into the all areas which is supposed to do, and all these are very critical for the manufacturing. Painting. How do you do painting of these bodies? So how much layer, how much pass it needs to do. So all these are very important for quality. You see the speed at which the robot moves, the angle, the distance between the body and the nozzle, the thickness that finally the body is going to get. Every aspects are important when you are creating this twin. Now, the twin can be for a CNC programming, could be for a robot, which is actually for an additive scenario. And it could also work for human combination together. So have a person working. So is that a 50 percentile South Indian male or a female able to work on this? Is this the height sufficient? So what are the problems which could be there, if the height is not correct? So are there injuries which can happen on the shop floor because it is not ergonomically correct? How frequent these operations can be? If that requires for a change in design, how well you're going to change your design? How do you create your electronic work instructions and provide this information across so that for the right part, the right instructions get displayed, maybe from a MES screen or a electronic work instruction screen, which is there. You can also look at how AR can help in performing the assembly or disassembly. So you can see that as the display happens, there is a camera which is there, but then the camera also augments the digital and the physical. So you have the physical coming in from the camera, the digital is also going into the software to know that what step the operator needs to perform, right? So you can also have the digital human with motion capture toolkit to exactly predict what what the operator is. So you can create a twin of the operator very closely. So, then it becomes very close representation of the real operator. And then use this twin to understand because this has the anthropometric data, and I can compare with the standards, that is that a right posture, and how long he can be in the current posture, and whether he's susceptible to any injuries because of this. All these aspects could be studied and improved. As I mentioned, you can also create a digital twin of the production. So in this case, a brake assembly. So you can see that each of the part has its own PMI, or a product manufacturing information. So you can see what the datum is there. So you can put this ABC, right? You would have studied in your metrology and measurements that what is the primary datum, secondary datum, tertiary datum. So, and how this how this process parameter is defined, cylindricity, where the datum is. You can see that the earlier, that was the tertiary datum. And what is the primary operation? So the primary operation becomes the phase, the base operation, and you create all other operations based on the primary operation, and then you have the jobs which are completed for the machining, and then you are taking it for the assembly. Now you take it for the assembly, and you can also do a virtual assembly, and this virtual assembly gives you ability to look at how well the production is going to happen. So if there are failures, can you produce this at a 6 sigma level, 3 sigma level? If there are problems, you can look at the Pareto to look at high, low, medium simulation to identify what is the process parameter which actually creates the problem. So you can run the virtual quality to see that how well we are able to improve. So we saw the robot, we saw the machine, we saw the painting, saw the human, but you can bring this whole thing into one play, and you can actually operate the complete plant. Okay. So the complete plant, you are able to simulate it, because you may want to improve the overall productivity. You want to identify the capacity. Is there a machine's sufficient or not? What should be the batch size? What should be the shift that you need to operate? How well you need to modify or change your sequence. What is the economic order quantity? So a lot of questions which are there. You may teach, in your operations research or production planning. So you can use these digital twin to operate. The size of the plant could be, as large as, anything. It could be for a SME, but then you are able to create the twin of the plant. Then it becomes a huge benefit, because you are able to optimize it. Otherwise, if you're making some suggestion, doing some changes, improvements, only when you try it out, then you know that whether it is going to bring change, or whether it's going to bring improvement or not. But once you have the digital twin and you calibrate with the present, which means the digital model is as good as what is running on the shop floor for a manufacturing unit. Now you can actually digitally change. You can even calibrate with your previous month data, saying that this is the current sequence which was done in this shop floor, and I operate it, and you get the same time. Now, if you would have done, so here in this case, you can run through the optimization, like, the neural network, or, various other, optimization scenarios. You're able to optimize, and then give a solution which could be far more, improvement in their productivity or capacity utilization. So huge amount of benefits which are there, which when you are able to create the digital twin, and you're able to capture this information from the physical system. So here in this case, earlier it is completely digital. Now you are connecting these informations from the shop floor, and you're able to get this data, and you are able to have the data twin, and bring these two pieces together. So both the data and the digital together, and with the twin you have the IT and the OT coming together. And to bring this OT data, you need to bring this information from the field devices, control edge, and finally either to the cloud or to the or the implant data systems. Now this has a lot of advantages. as I mentioned, it could be for process optimization. So in this case, what I'm taking as an example is even in the food processing, there is a level cut which needs to be achieved, like, the profile which needs to be achieved, and you can use this twin to improve that. So it is limitless, like, it could be for a textile industry or a food manufacturing, or it could be a chemical, could be a variety of industries. But what you're able to do is the extrusion which happens from this machine, and you are able to online improve to the level where, like, there is a significant improvement in the quality. Otherwise, there are quite a bit of rejections which happens. Now, how well you are able to use this twin to minimize or avoid those problems related to quality. Could be, like, as you can see, the physical performance, you're able to connect with the digital twin to put this in the digital world itself. And here there is a shovel assist system. So there is a twin which is actually operating in the edge level. So here in the edge level means there is a control which is there in this with the operator himself. Now, how will these buckets need to perform at the edge layer? Because we need not that once the data is there, what could have been done. See here, this is a very good representation. If you see that this is on the ports, there are containers, right? So there are containers which are there, multiple containers which are placed, and I need to place this container close to this, because I have a constraint related to space and the location, how this is going to get picked up. Now, typically what happens is, there is, because of the variation, there is always a slight accident which happens. It hits and then it comes back and all that. Now here with the digital twin, the image is already available, and that the speed at which it can go, where it needs to brake, and how it needs to place, those things can be much better handled when you're having the digital twin. This is something which we did in one of our factories, where this is the PCB cutting happens, and as it goes for a few weeks, there is a dust which from the board which goes into the spindle, and there is a failure. Basically, what happens is that need to remove the spindle, remove the dust, and then start the production again. So the issue, what happens is, because this can happen anytime, then the production needs to stop, and the problem is costing the production. Now, what we did is did the anomaly detection with the edge device. So identify that whenever the dust level increased, actually it causes increase in the current consumption. So the moment we see that the current consumption cross certain threshold, you're able to identify that before 2 days in advance, that you're able to identify the failures, and which eventually, like, help to avoid the production failure, and you're able to use it by the maintenance. And this could be cleaned up probably, like, on the regular maintenance level itself. So the whole idea of digital twin is it is for both product and production, and it needs both the real world and the digital world together. And it is an evolution. So we saw with 2D design, 3D design, 3D simulation, multi-domain, AR, VR, IoT, and then you have the digital twin, and the digital twin powered with the AI, with the executable digital twin, which is actually, like, going through the optimization on a real-time basis, eventually going through a metaverse with NVIDIA Omniverse capability, and then the shop floor side. The top one you are seeing from the digital, bottom one, we are talking more from the shop floor with the industrial edge and visual controller and so on and so forth. So that, in summary, is my foundation for the digital twin. So as a whole, what you are able to do with the digital twin, the benefits is you are able to learn from the past, you are able to optimize the present, and you're able to predict the future. Somebody can put it on the chat window. So I'll be happy if you're able to remember these things. Thank you so much.
So thank you, sir. Dear participants, do you have any questions? Kindly unmute and ask the question.
You can see some questions. How will the digital twin correlate with the physical system? Yes, this is really important. And how well is the process? So this is how close we are able to have the digital twin is something that that you need to decide, because you can get as close as possible, but what close is practical is where you need to stop, because uh, why you are doing this digital twin will be the one which will be driving that how close you need to correlate. Okay, you can do it at say 99.99%, or if you are able to do it right now with the current system, you are able to get majority of the benefit or 80% of the benefit with even say 90% correlation. Then go with the 90% correlation, because the last 5%, 10% may not yield a huge level of advantage compared to the cost. So it depends what you want to do. How do you reverse engineer to create the digital twin? So, I mean, today you have huge amount of tools to do the reverse engineering. Depends on what you want to reverse engineer. You are reverse engineering the PLC program, or you want to reverse engineer the physical geometry or the plant. You have tools very specific for that. That question from Mr. Virender Singh Thakur. Okay. So you ask, so if you ask what you want to reverse engineer, I can provide the answers for that, Mr. Thakur. A DC motor machine, okay. So you can send that. I will provide the details, like how. What this representation needs to be and the purpose of it. So if this purpose is to determine the say failure prediction, so I can provide the details how you can do that. Thank you. Sure. I can send this across to the coordinators. I can send the details.
Yes, sir.
Okay.
So, thank you, sir. Sir, you have explained about the digital twin with the help of real industry scenarios. So, very well. Your session was very nice. So, we have to conclude the session. So, on behalf of ISTE, BNY, and Knowledge Institute of Technology, we very much thankful to you, sir, for sparing with your valuable time with us. Thank you, sir. Thank you once again, sir.
Thank you. Thank you so much.
Thank you so much, sir, for accepting our invitation and having your time here today.
Thank you. My pleasure. Looking
Thank
forward.
you so much, sir. Thank you so much.
Thank you.
Thank you, sir.
So, dear participants, one announcement. We have break the session now. So, we have take the 5 minutes as break. And then all are requested to join 11:55 a.m. The next session 2, will start at 12 p.m. sharply. Thank you.
The topic is digital twin development workflow. Okay, so just I'm going to talk about the important components of the digital twin and how the workflow will happen. So all those components we will discuss. Also, this is the outline of the talk today. So mostly I will just again start with the basics of digital twin, and so all of you know that this is one of the very most important technology of industry 4.0. Suppose so we will see the how the concept of digital twin is evolved, and then mainly I will talk about the digital twin development workflow. Then if time is there, little bit we'll discuss about the industrial applications and case studies. What are all the future trends? Then I will summarize my talk. So this is the idea of the talk today. Um, so now we will start with the what is the digital twin. Already, I hope you may know the definition. Suppose you imagine, so if every machine or manufacturing process, aircraft engine, or even a entire factory, if you take it, it had a virtual replica. suppose that could predict the failures or optimize the performance of any process, and continuously it can learn from the real world data. So that concept is basically, it is called like a digital twin. Okay, so it is a something like it is a transfer, the digital technology, the twin technology is transforming industries in such as manufacturing, aerospace, particularly nowadays in healthcare industry, and smart cities. Okay, so in this session, we will try to understand the what is digital twin and how it works, what are all the major components, and why it is becoming very essential for the modern engineering system. We will talk about it. So, as per definition, already you know that it is a virtual representation of the any physical object or system or process that continuously receives the real-time data from its physical counterpart. So that is basically a definition of the digital twin. So it can be a virtual replica of physical system. Already I told you. So continuously it will update the data from the real-time data. For that we need a physical object, right? So always this physical object and virtual model that should be remain connected through certain kind of sensors, communication systems, and data analytic platforms. So we did for that. Okay, so suppose for example, if you take the traditional simulation model, so always the digital twins are dynamic and continuously it is evolved with the real world system. Okay, so this is the basic concept of digital twin. For example, if you take the traditional approach, so industries basically traditionally, if you take, they will react to the problems after they occur. So usually, suppose certain operation is going on, so only they will try to understand the particular failure of that particular process or machine after it get repaired. Okay, so that is a traditional approach. So once it's got repaired, they will try to rectify it. But in case of digital approach, so basically it allows the organization to predict the failure before they happen. So in that way, we can predict and prevent the particular failure, and also we can optimize the process. So in that way, we can reduce the downtime and improve the productivity. So this is the main idea. So for that, we need a connect this physical system with the digital model. So for that, we are using the sensors and data communication. So these things are important. Okay, so this is the basic concept. Okay, so first then we have to understand about the physical system. What I'm trying to say, physical system means here it can be a machine. I don't know whether I could able to write or not. Okay, I think I could take right. So here, what I'm trying to say is what is physical system means. So it can be a, suppose maybe a machine, or it may be a, suppose if you are applying for the aeronautical engine, okay, or it may be a some robot or manufacturing process. So in that particularly, we have to attach the sensor to collect the real-time operation data. Okay, so suppose, for example, some kind of CNC machine is there, some machine is there. We need to understand about the particular real-time operation data. So what can be the real-time operation data? There might be some kind of what is the speed of the particular engine, right? So speed, or you may measure the what is the pressure in between the tool, and what is the interaction with the work of the component, or what is the vibration. So these are all the uh, processes. So for that, to take this data, we need a sensor to in order to identify the speed or vibration, temperature, all those things. We need a sensor. Again, the sensor should send the data that can be transmitted through the communication technology. So communication technology nowadays, a lot of communication technologies are there, like kind of IoT networks, cloud computing, or edge devices. So you can use this some kind of this recent communication technologies. So in that way, so the digital twin or virtual model will receive the data and continuously it will update itself. So using this analytics or simulation, we can able to detect the any of the fault, or you can optimize the process. So it basically it recommends the optimization strategies. So in that way, so this is the basic concept of digital twin. So just by example, I am trying to explain. Uh, Suppose this is the historical background of this digital twin. So nowadays it is really it is becoming popular recent years, but already it is existed for several decades. Suppose, for example, briefly, if you look at the evolution of this technology, the journey begins in the year 1960s. During that time, basically it is a space exploration era. It is called it like the organizations such as NASA. They basically develop the physical replica and simulation models of spacecraft systems. So during their missions, the NASA mission, the engineers use this kind of ground-based models to understand the behavior and troubleshoot the problems remotely. Those things they have done it. So this is the basic first step towards this kind of digital twin concept. After that, moving into 1980s, 90s, so you can see the already we know that, right? Like kind of the CAD, the computer aided design is boomed at that time. Also, the it enabled the kind of engineers to create the accurate digital representation of products before manufacturing them. Also, you can virtual prototype become very common in industries, right? Like for example, automotive or aerospace industry. So the virtual prototype become very common in 80s and 90s. So engineers can good evaluate the designs and also perform the simulation, also able to identify the potential problems without any kind of building the physical prototypes. So that is the main advantage happened. After that, the major milestone happened in the year after 2000. Okay, 2002. This concept was first proposed by formally proposed and introduced by this Michael Grace. So he proposed the kind of idea of creating a digital representation of a physical product that remain connected through its entire life cycle. So, for example, his vision basically he included the three basic key component. One is physical product, second component is virtual product, and next is the data that connects the links the both. Okay, so in that way, so he connected this all these key components. So at that time this concept was very revolutionary, and the technology is basically it's required to implement to a larger scale was still basically it is limited. So then, next major advantage if you take advancement if you came during the year 2010. So because at that time the several technologies got simultaneously got matured. For example, the sensors become very cheap, and also the data what we can get from the sensors are more reliable nowadays. So also the IoT, the Internet of Things, enabled real-time connectivity between the devices, cloud computing. So all those concepts like kind of matured state in recent years. Okay. So in that way, this big data analytics allowed the organization to process the enormous volume of information. So this development basically transformed the digital twin from a theoretical concept to a practical engineering tool. So if you take the uh, digital twin nowadays, so almost it is used in many industries. For example, manufacturing companies use them to monitor the many of these machining operations and predict the failures. Aerospace, if you take to track the engine health, they are using it. Suppose if you take energy companies, they use to optimize the wind turbines, power plants. Also, the health care industries are using for develop the digital twins of human organs and patients to support the personalized medicine. So these things, concepts and all nowadays, people are focusing on more towards the region advancement. Uh, so this is the future. Future is autonomous and self-learning digital twins. For that, it is going ahead. So already we discussed about this. Uh, historical background. Now I'm just going to so why it is important. The digital twin concept is why it is important. So always, if you see the concept, the misconception is that digital twin is simply a 3D model. So in reality, basically it is more than that. So suppose if you take a CAD model, it shows them only how the object looks, right? So also the simulation model, if you take, it will predict how it behaves under some specific condition. Also the but here the digital twins basically it combines these capabilities with real-time data. That is the advantage of that. So from the physical system. Okay. So in simple terms, if I want to say, so basically, this digital twin is a living digital replica of a physical asset or process or system. We can take it any of that. Okay, so it will continuously receive the information from the sensor, interrupt from the data, and also we can analyze the performance, feature behavior, and also it will support the decision making also. So this many things we can do it by the digital twin. So most important feature what it will distinguish from the traditional model is basically it is a continuous synchronization. That is the main feature it has. uh, Also it has the physical asset has certain challenges, so we will see that for in later part. Okay, so basically it has the capability to basically transform the reactive approach to a predictive or proactive approach. So that is the main why the digital twin is important. So also suppose it helps the industry in many ways. Okay, uh, for example, it can reduce the downtime, predict failures, optimize the energy consumption, and also the product quality, reduce operation cost. So these are all certain advantage for the industries. Okay, so in modern smart factories, so digital twins becoming a basically a backbone of intelligent manufacturing. Okay, so that's what we can take it like this. So this is the main characteristics of the digital twin. The first one is, if you take first one is the real-time connectivity. So the physical system, so basically the system continuously sends the live data to the digital model. So that is called it like a real-time connectivity. Second is the continuous synchronization. It means the virtual model updates itself dynamically according to the operating condition, like what are all the process condition. Accordingly, the dynamically it can optimize. So that is the continuous synchronization. The third is the virtual representation. So here, so basically this digital twin accurately, it can represent the geometry or behavior or performance of the real system. So it can be anything, like it can be object or behavior or performance. So any of the real time system, it will easily it can represent that. So that's why the virtual representation is also one of the main characteristics. Okay, fourth is the predictive capability. So nowadays all of you know that because of this AI and simulation softwares, so it can predict the failures and future conditions. Also it can take the decision making also. Okay, so fifth is the two-way interaction. So what it means is not only the physical system will send the data to the digital twin, but the digital twin also can send the optimized control commands. That's what I told, like it can send the based on the correction, so it can send the what is the optimized control commands back to the physical system. It can send it. Okay, so that is the also one of the main characteristics. Last is the finally the life cycle management. So for example, life cycle management means so it can support the system from any of the design and manufacturing to operation and maintenance. So almost whole life cycle it can support the starting from the design to the manufacturing, operation, and then maintenance. So it can totally it can do it. So okay, so now let's discuss about what is the main component of the digital twin. Then we will go ahead with the what is the digital twin development workflow. Okay, So first we have to understand these three main components. Then only you will get the idea about what I'm talking about this workflow development. Okay, uh, so now we need to understand these fundamental components that work together to create a digital twin. So simplest level, so this is the three components it has. So for example, if you take physical entity, so that is the real world system. Okay. Uh, for example, here the virtual entity means that is a digital representation. Data connection, what I mean here is it is continuous. Data connection will continuously exchanges information between the physical entity and virtual entity. Okay, together they can create a kind of dynamic system that is capable of monitoring, predicting, and optimizing the all these performances. Okay, now let's start with this uh, first component, physical entity. So physical entity is basically, it refers to the, already I told, it is an actual physical system or object. So suppose, I don't know whether, so it can be object, it can be a system, it can be a machine, okay, it can be a process. So this thing we want to represent it digitally. So depending upon the application, so uh, we need to take the physical entity. So for example, here the manufacturing, here we have taken the CNC machine in a manufacturing plant. Okay, or suppose you can pick the robot on the assembly line. Okay, suppose you can take in the aircraft, maybe you can choose the only to monitor the aircraft engine, we can take it as a physical entity. Okay, so in that way, in many process, we can take any of this component, whatever you want to monitor, that we can take it as a physical entity. Okay, so there basically uh, all these real world activities will occur, like it perform the operation, or it consumes the energy, or it may generate the data, performance data. Okay, so to build the digital twin, so we must first understood the physical system thoroughly. Basically, we need to understanding its design, operating condition, what is the material properties, what is the performance, failure mechanism, all those things we need to understand. So, for example, I'll take the CNC machine here. So, suppose you want to create a digital twin of a CNC machine, so we need a information about all these components, like kind of we need a spindle speed, cutting forces. Okay, so what is the cutting forces, and what is the tool geometry? What is the tool geometry, and what is the operating temperatures? What is the operating temperature, and what is the machine structure? So these things we need to understand. Like more accurately, we should understand the physical asset that is more reliable. How our digital twin will be. Okay. So again, uh, so this system will generate a lot of operation data. These parameters we need to, so basically, it should give the variable information about the condition of this particular physical asset or entity. So that we need to be careful. Like what are the parameters are important, we have to take it. Like means, for example, if you take CNC machine, so their temperature, pressure, vibration, force, speed, this kind of parameters are important. So we need to collect this data. Okay, so also next we need a digital environment. So where this information can be interpreted and analyzed. So that basically brings us the second component. Okay. So already I told about this. So what are all the things we need to understand in order to build the physical entity? So we need to understand about this, all these parameters, geometry, properties, material condition, maintenance history, performance characteristics. So this thing, in that way, clear understanding of these things can build the physical system. Okay. Now let's move to the virtual entity. So here, in case of virtual entity, basically it has models, simulations, databases, and analytical tools. So that can help us to understand and predict the behavior of the physical system. Okay. So, for example, the first part of the virtual entity is usually a geometric model. Already, what are the geometry of that physical entity we need to generate. So that is often how we can develop. So already we are mechanical engineers. We may know about this, right? Like how we will make the design by using any of the CAD software. We can make a geometric model. So by using the SolidWorks, ProE, CATIA, so many softwares are there. Okay, so the geometric model basically what it will tells, it tells about the shape, dimension, what kind of assembly details of the physical asset. So this can be understand. So once uh, uh, doing it, this is the first part. To understand about this geometric model is the first part. So next is the second part is the physical based models. Okay, like it also consists of physical based models. So this model basically describes the how the system behaves under different operating conditions. Okay, that is the second thing. So, for instance, I'm just taking the structural model, so that can predict the stress and deformation. Okay. Uh, Similarly, suppose if you take the thermal model, that can predict the temperature distribution. So, like this way, it has to predict some kind of operating condition based on the physical based condition. It has to develop. So, this simulation also will help the engineers to understand not only what is happening, but also what may be happen in the future, like kind of prediction it can do. Okay, this is the second component what I'm talking. It's like last is the important component, that is about the virtual entities, the historical data. Okay, so basically this digital twin should store the all the operational history, production data, and previous failure events, maintenance records. So this historical information basically it provides the context and helps identify the trends that may not be visible from the real-time data alone. Okay, so that is also one of the important component. So if you take a modern digital twin, basically it will incorporate the AI or machine learning algorithms. These algorithms can analyze the large data of historical data, detect the abnormal patterns, estimate the useful life, and recommend the optimal operating conditions. So in that way, so virtual entity is just more than 3D model. I can say that it combines geometry, physical data, and intelligence to create a comprehensive digital representation of the physical asset. Okay, so uh, so this is the basically a brain of the digital twin where modeling, simulation, prediction, and analysis will take place. Simply, if I want to say, okay. Uh, So to summarize, so this is the basically this digital twin is built upon this essential components. Physical entity will represent the real world asset or process. The virtual entity basically it contains the digital model, simulation, databases, and intelligence required to analyze the data behavior. So already I told about this geometric model. So here the geometric model, these three things it will describe shape, dimension, and assembly structure. But in case of physical based model, we can use the any of these engineering models to understand the system behavior. So, for example, already I told you stress analysis to understand the deformation or how much stress is uh, developed. Like deformation prediction, we can do. Like by using the heat thermal models, we can understand the how much temperature is distributed and heat transfer problems can be understood. So, in that way, the engineers can simulate the real world behavior under different operating condition. So finally, so we need a historical data also, one of the important entity. So because it records and maintains the logs, failure history, production record. So this basically to identify the trend and patterns that cannot be observed from the real-time data alone. Okay. Now fourth is the nowadays AI and ML. These models are basically we are using these algorithms to help this understand this anomalies, to detect the anomalies, predict the failure, and estimate the what is the life cycle of this particular physical component, or optimize the process parameter. So this can be done. Okay. So in that way, so digital twin from a passive model into an active decision support system. So it can transform. Okay. So now let's move to the what is data connection. So data connection is nothing but basically it continuously synchronizes the information between the physical and virtual world. So suppose with these three components work together, then this digital twin will become a powerful tool for a kind of real-time monitoring or performance optimization. So this understanding of these three components are really very important. So each stage of the digital twin workflow revolves around these three components, like building, connecting, and improving. These three components basically tells the workflow of the digital twin. Okay. So now let's like we are going to talk about this all those things. So in the next digital twin workflow, I will just show you. Okay. So these are all, we will talk about it more about it. That's what I'm going to do it in the digital twin um, development workflow. Okay. Um, so for example, if you take here the data connection, so basically it ensures the virtual model always reflects the current condition of the physical asset. So for example, here sensor, IoT devices that will connect the operation data. Then the communication network means nothing but it's a kind of transfers the data through some kind of cloud and network technologies. Fourth component is a edge platform, right? Or virtual model. There, so you will model will be developed using the some kind of CAD models, and by using the FEM, you can analyze the you can do the system analysis. Okay, AI based models. So finally, visualizations of this such as these interfaces such as dashboards and 3D platform that help the engineer to monitor and control the system. So that is basically a overall how the digital twin uh, evolves. You can see it. Okay. So now I'm just going into the digital twin development workflow. So now I hope you understood the what is the concept, what is the how it's evolved, and what is the components of important components of the digital twin. Let us now discuss about another aspect, like how actually digital twin is developed. Basically, already I told you it is not simply creating a 3D model or connecting to sensor. It is a systematic process. Basically, it combines the knowledge, engineering knowledge, or communication systems, or data analytics and artificial intelligence. So these things are needed in order to develop the digital twin. So okay. Uh, so now first important step in developing a digital twin is the so we need to define the objective. Okay. So these are all the steps. You can see that one by one we will try to explain this. Okay. So now let's start with the why defined objective. Okay. So always, if you take the any twin project, so basically it will begin with the clear understanding of the problem. Suppose what we want to solve. Suppose the technology should never be a starting point, or engineering need should be like many organizations. Suppose if you take it becoming exacted about this digital twin technology, so but immediately they have to begin collecting data. Okay, without clear any kind of objective, they often end up with the large data sets. We cannot do anything with that. Okay, first we have to focus on the so why we are developing the digital twin, and the goal is to improve the mainly to improve the machine reliability and also to reduce the maintenance cost, and also increase the productivity. Okay, so second is the like what kind of outcomes are expected, like for example, suppose we may want to reduce the downtime by 10% or 20%, energy efficient by 10%, like this. Okay, suppose you want to increase the certain lifespan of the equipment. Okay, this is the outcome. Third is the what asset or process will be represented. So, for example, single machine or entire manufacturing process, or it can be even entire factory, okay, or entire city. So, what you want to like kind of represent, that you have to be very clear. Okay. Again, fourth is the what decision will be uh, supported, or what decision will be the digital twin support. Okay. For example, will it help for schedule the maintenance or optimize the process parameters or predict the failure or support the autonomous operation? So these things and all we have to be clear. First, we have to define the objective. Okay, maybe I can explain with certain example. For example, we'll take a CNC machine again. I hope all of you know about the CNC machine. So we'll take that. So suppose the manufacturing companies experience frequently tool failure, unexpected machine stoppages. So in that case, so the objective should be like to predict the tool wear and reduce the downtime and improve the machine quality. So this objective basically uh, determine the everything that follows. Suppose sensor selection, data collection strategies, modeling requirement, and performance matrices. So therefore, defining objectives establish the roadmap for the entire digital twin project. Okay, so that is the first thing. So next thing is the we have to understand the physical system. Okay, so once the objectives are established, the next step is the understanding the physical system. So because already we know that the digital twin cannot be more accurate than our actual understanding of actual asset. Okay, so before building the any digital model or collecting data, engineers must thoroughly understand the physical system. Okay, they suppose they want to intend to replicate that thing. So in that way, we need to completely understand the system. So again, so we can gather the information again by geometric case CAD models. We can use it. Performance for that we can use the any kind of software. Suppose you want to understand the deformation, then you can use a FEM. Thermal analysis, thermal models, you can use it like this way. So also you have to understand about the material also, what kind of material you are going to use it. uh, then material condition also very important. These things are uh, very important. Okay, apart from that, historical information also equally important. So for example, maintenance records, failure reports, infection data. So this will give some kind of insight into how the system behave over a particular time. Okay, so in that way, suppose if you're developing a digital twin for any of this CMC, so we need to understand this about the all the parameters like pressure, temperature, wear. So all this behavior also we need to, environmental condition also we need to understand, like spindle characteristics, cutting forces, vibrations, tool wear mechanism. All those things we have to understand. Okay, so this is about the how you understand the physical system. Okay, step three is the basically a data acquisition strategy. Okay, so data acquisition means nothing but so here the objective here is to not to collect the entire possible parameters, but to collect the right parameters. That's what I told. So we need to choose what is the right parameters we need to understand. Okay, so we need to understand what is the critical variables. For example, what are all the variable will affect the performance or reliability or health of this particular machine. That parameters we need to include. So, for example, CNC means temperature will affect this thermal health, vibration will affect the machining condition, speed will affect the operating status, current will affect the electrical health. So, like this way, you can understand about this common parameters. Okay, like from that you have to choose what is the right parameter. We have to choose that. Then only you can do a process optimization, like kind of what is the parameter you want to optimize, pressure, force, or energy consumption. So more relevant things can be must be selected. Okay. Also, next step is we need to select the appropriate sensors. Then it has to identify accurately. It has to identify the parameters. These things are very important. Okay. Vibration monitoring, again we can do it by the accelerometer. Temperature monitoring you can do it by thermocouples. Force measurement you can do it by kind of load cells, right? So these things that are we know. So also the placement of sensors also play a very important role. Like poor placement of sensors may give some inaccurate measurement or unreliable data. So that will significantly reduce the digital twin performance. So we need to take care of this, all those things. Acquisition strategy, data acquisition strategy, we have to uh, uh, very important. Okay, next is the communication infrastructure. Uh, Communication infrastructure means nothing but once suppose the data is collected, it must be transmitted reliably to a from the physical asset to the digital twins, right? So this requires a kind of communication infrastructure. So for example, typically the sensors and the data acquisition systems or PLC or edge devices or gateways, right? So this information is basically transmitted through this communication protocols. You can see that MQTT, Modbus, Ethernet, through that wireless network, so you may send the information, right? So many application, if you take edge computing, is used to process the data locally before sending relevant information to the any platform, cloud platform. So reliable communication is very essential. Okay, so once suppose if the data communication or transmission is delayed or interrupted, digital twin may not be a no longer uh, accurately represent the physical system. Completely, it may lose its strength. Okay, so the communication infrastructure is really needed. Next is the data storage and management. Okay, again, uh, nowadays the modern industries are generating a more amount of data, like kind of enormous quantities of data. But so suppose, for example, the single machines can produce thousands of sensor reading at every second. Okay, so this must be data should be stored, organized, and managed efficiently. So for that we need a data storage. So that can be performed by local servers, cloud platforms, or hybrid architectures. Okay, so again, cloud computing has become a very important because uh, it kind of offers the scalable storage or powerful computation resources. Okay, so this is the fifth step. Next step is virtual model development. Okay, building a virtual representation of the physical data is called it like a virtual model development. It is one of the heart of the digital twin or core of the digital twin. We can call it like that. So because already know that the first common is the geometric model, because geometric model will tells about the shape and structure of the asset. Next, second component is the physics based model. Physics based model, we can understand about the how the uh, various operating condition, how it behaves. So for example, already I told you FEM software or some kind of CFD simulations, we can use it, or dynamic models. Okay, dynamic models, we can use it to analyze the different parameters, right? So third component is basically it consists of data models that stores this historical and operation information. Okay. Finally, basically the digital twin include the artificial intelligence model because that is capable of learning from data and generating prediction. Okay. So in that way, so you have to describe the system behavior or understanding the system behavior. That is very important. Okay. Next step is the uh, physics based simulation. Otherwise, I can say like simulation. So simulation is also very important, right? Like that models will help the understand the performance under different conditions. Already I told about the CFD, thermal softwares, dynamic analysis. So what is the use of that is shown here. Step 8 is the data integration and synchronization. Okay. So data integration. So here various sources of information must be integrated into a unified digital twin environment. So, for example, digital twin combines the real-time sensor data or simulation outputs, historical records, and operation information. So here the goal is to maintain the continuous synchronization between the physical and virtual system. So whenever the physical asset changes, the digital twin updates accordingly. So that is the main idea. So synchronization, it has to do it on time. So for example, if machine vibration suddenly anomalously increases unexpectedly, the digital twin immediately reflects this condition and update the prediction. Okay. Whatever the anomaly in the process, suddenly it has to update and it has to understand. The synchronization is for that, it's very important. So that transform the static digital model into a living digital twin. Okay. So for that, we need a sensor data, simulation data, historical data, maintenance records. So all those things are needed that will create a digital twin intelligence. Okay. Uh, Next, last is the now AI or advanced analytics, artificial intelligence. Nowadays, the it is adding the intelligence or predicting capability of this digital twin is enhanced because of this AI or machine learning algorithms, because it could be able to predict the large number of data, right? Identify the patterns and relationship. So maybe we cannot understand by the human cannot understand virtually, but the ML algorithms or AI algorithms easily can identify the some kind of patterns or relationship that is existed between this operation. It can easily predict it. Anomaly can be predicted, quality prediction, process optimization. These things and all can be easily, it can uh, do that process. So in that way, we can do a failure prediction or early fault identification. We can do productivity also will increase. Finally, the lifespan estimation also will enhance. So these are all advantage of using the AI and advanced analytics. Step 10 is the validation and verification. Okay. So before deployment, that our digital twin should be validated to ensure it's whether these predictions are accurate or not. So this validation basically involves comparing this digital twin output with the actual measurement from the physical data. Okay, like we can measure the data. So for example, if digital twin is predicting the CNC spindle temperature is something like 140 degrees Celsius, but the measured value is 142 degrees Celsius, then we can still the model accuracy is acceptable, right? Like we can say that you can use the any kind of metrics as something like root mean square error or mean absolute error and correlation and coefficient to quantify the performance. So what I'm trying to say is, so it is very critical. The validation is very critical because inaccurate prediction may lead to a very poor decision. Also, it may cause some operational risk. Also, it may cause. So validation and verification is very important. Okay. Next step 11 is the deployment, and I can say that continuous improvement. So once suppose the data is validated, uh, then this digital twin is deployed for operational use. Okay, system will be connected to a dashboard that may provide the real-time monitoring, alerts, decision support tools. So anyway, the deployment is not only the end of the journey. So because digital twin is continuously evolves throughout the life cycle asset. So this may create a continuous improvement cycle. So like kind of real-time monitoring, 3D visualization. So already these things I told, like it can be monitor, it can predict, it can optimize, it can update, right? So in that way, the digital twin is becoming a smarter and more valuable. Okay. So again, to summarize this digital twin development workflow, so we always already I told you it begins with the uh, defining the objective and understand the physical system. First point is, and next is we have to develop the virtual model. Then the virtual model is combined with simulation, AI and analytics. Then once AI is predicted, the digital twin is validated, then continuously improved throughout the asset life cycle. Okay, so then only you can understand the true power of the digital twin, uh, and also so we can optimize the any of the process, or it can support the any intelligent decision making. Okay, uh, so so now let's uh, discuss about this how the enabling technologies for digital twin. Already we have talked about this components already. Quickly, we'll talk about this. What are all the enabling technologies for digital twin? So basically, these are all the uh, things are integration of the multiple advanced technology. For example, IoT, sensors and data acquisition, cloud computing, big data analysis, AI, ML, edge computing, simulation and model technology. So this enabling technologies we need to understand a little bit about it. So then only we can choose uh, among these enabling technologies. Okay, so for example, I start with the IoT. So IoT is nothing but it is a network of interconnected device that can collect and exchange data. Okay, so it means real-time data collection. It can do also continuous monitoring, connectivity between physical and virtual systems. So these are all certain functions in the digital twin. Okay, so without IoT, the I can say that the digital twin cannot able to receive any kind of real-time information from the physical system. So mostly certainly it needed to maintain some kind of communication bridge between the digital and physical worlds. Next is the sensors and data acquisition. Okay, already I explained it. So quickly we are just talking about this enabling technologies. Uh, Suppose sensors, basically it's very important because it's always called as eyes and ears of the digital twin. Okay, because that basically gives the real time or real world information required to understand the what is the current condition of the physical asset, right? So for example, already I told you like what are all the sensors can detect the different process condition. Thermocouple can detect the temperature, or accelerometer can detect the vibration. So all those things I explain. Mm. Next is the cloud computing. So again, cloud computing. If you come here, so nowadays these modern digital twins can generate the much amount of data, but uh, uh, for example, already I told the single machine can produce thousands of measurements in each second. managing this kind of data is really very difficult. So that's where the cloud computing becomes essential. Okay, so not only maintaining the local servers, it can use the cloud servers to store the running the simulation or historical data and execute the machine learning algorithms. Okay, so in that way, so it can provides the scalability and computational power necessary for the large scale digital twin implementation, like kind of large scale data storage, remote accessibility, scalability. These things are possible by cloud computing. Okay, so some of the examples are shown here. Next is the big data analytics. Again, big data is the data is always described using the concept of big data. Again, we can characterize this big data by five V's: volume, velocity, variety, veracity, and value. Okay. Uh, so here, the big data is basically helps to identify the trends, patterns, correlations, and anomalies hidden within the massive database. So, so this also very important in that point of view. For example, if you take analytics may reveal the particular vibration pattern consistently occurs several days before machine failure. So these anomalies can be easily can be understood by the big data analytics. Okay. So next is the already we have talked about much about the AI and machine learning. Maybe again we little bit will discuss. So AI basically it transform the digital twin from a monitoring system into a intelligence system, decision support system. Uh, uh, Traditional, if you take traditional system, so that can tell us only what is happening, but AI will help us to understand why it is happening and what is likely to happen next. So in that way, we can analyze the large data sets to identify the hidden patterns and relationship between the process parameters that can be understood. Okay, like for example, if you take any kind of machine learning models, they may learn the uh, any of the characteristics of the machine. Suppose the vibration characteristics associated with the what is the wear mechanism. So by using the simple pattern, what is appearing in the real time data, so it can predict the failure and also it can warn the system. It can issue a warning. Okay, so in that way, so it can also estimate the life of the component and improve the product quality, also reduce the energy consumption. Okay, so nowadays this AI and ML become a very core technology responsible for predictive and autonomous capabilities. Okay, next is the edge computing. Again, edge computing is nothing but um, it addresses the challenges by processing data closer to where it is generated. So, for example, the machine manufacturing machine may have a edge device installed nearby. Okay, so instead of sending the every sensor reading to the cloud, the edge device perform the initial processing and only transmit the whatever the record information is needed, like important information, only it will send. So it reduces the kind of latency and enables faster decision making. So in that way, autonomous system and real-time industry control application, it can be really useful because the response is very faster and the reliability also really very high. Okay. So next is the simulation and modeling technologies. Nowadays, a lot of simulation technologies are there. Like already we talked about FEM, CFD, thermal acid dynamic simulation. So these engineering models can allow the digital twin to evaluate the scenarios that may never have occurred in reality, making them powerful tools for prediction and optimization. Okay. Uh, Next is the what is the integration of technologies. So here um, the sensors can collect the data. The IoT enables the communication, and cloud and edge platform process the information, analytics, big data analytics or analytics extracts the insights, and AI or ML can generate the predictions, and simulation models provide the engineering understanding. So together, basically, they can create a digital twin capable of monitoring, predicting, and optimizing the system performance. Okay. So to summarize, what I can say is, so this enabled technologies basically plays a very important role, and together they can transform the physical asset into intelligent or predictive system. So that's what I want to say. So now let's talk about some of the industrial application and case studies of digital twin. So already I told many of these areas it can be applicable. Nowadays, people are using it for the healthcare, smart cities, transportation. Okay, so so many of the areas people are using it because so already so one by one we will discuss basically. Um, because it can the key benefit is really uh, good actually. For example, it can reduce the operational cost, reliable, it can increase the reliability or improve the reliability, productivity can increase, and it can support the intelligent decision making. So these are all the key benefits you can see here. Maybe we'll start with the manufacturing industry. So already you know that if I tell manufacturing, it is one of the largest application area of the digital twin technology. Um, Suppose uh, so nowadays this digital twin changes this manufacturing industry approach completely from the traditional manufacturing. For example, it continuously monitor the machine conditions by using the sensors that can measure the various process conditions like kind of vibration, temperature, like that. So in that way, the virtual model analysis can get the information and predict the failure condition. Um, Also to help the optimize the manufacturing process. So in that way, this foundation of this smart factory concept, where physical and digital systems can work together to improve the operational efficiency. So, for example, if I take a case study of CNC machine digital twin, just I'm selecting the CNC machine as a machine center as a digital twin. Suppose already already I told about this example, right? Like suppose the tool wear is the one of the main problem, and also the unexpected downtime also happen in the CNC machine center. Okay, traditionally the tools are basically replaced after fixed operating periods. Whatever the tool wear does not occur uniformly, or the tool may fail earlier, whatever maybe we will fix the tool after certain fixed operating periods. So this digital twins basically address this kind of challenges by continuously monitoring this spindle vibration, cutting forces, and power consumption. All those things it's monitoring these parameters. So in that way, it can reduce the tool wear and also improve the machine health, process optimization. This can be done. Okay, so this is one of the case study I want to say. Next is the aircraft industry, also one of the pioneers in adopting this digital twin technology, because already we know that the always this aircraft systems are working under extreme condition. For example, it requires a high level of safety and reliability. Suppose if some failure happen, it may cause a very serious consequences, right? So in that way, this digital twin can help these aerospace industries to maintain this, continuously monitor the aircraft engines or critical structural component of the aircraft parts that can be monitored throughout its operational life. Okay, in sensors can be, again, sensors can be installed, and then it can measure this temperature, pressure, vibration, structural loading, all those things it can. In that way, it can predict the degradation, fatigue failure, maintenance requirement, all those things can be possible. Okay. uh, um, so for example, it can improve the reliability, lower operating condition, and also can increase the flight safety. Okay. And also, if you take the energy industry again, uh, energy industry also oftenly, like often operate continuously, and also geographically, if you take, it is distributed, right? So wind farms, power plants, solar installation, and electric grids, these are all coming under the energy industries. Okay. So for example, if you take a wind turbine, that experience constantly changing environmental conditions. For example, you want to monitor this wind speed, rotor speed, temperature. So this can be, the digital twin can analyze this wind speed, blade loading, what is the vibration. In that way, it can predict the failure prediction or energy optimization. In that way, it can improve the reliability and higher energy output. This can be possible. Okay, these are all the certain case study. Um, Again, if you come to the healthcare application, so so this is one of the most emerging application nowadays in the healthcare application, because people are nowadays, they are developing the digital twins of the patients or patient organs or physiological system. So kind of the patient specific digital twins, nowadays it can incorporate the medical imaging data or clinical records. So all those things can be possible in the healthcare industries now. So the doctors can simulate the treatment options and predict the patient responses, how the patient will respond based on the data, and before giving the any kind of administrating therapy. Okay. So also, kind of digital twin of this human heart may help the physician to evaluate the different surgical approaches and to identify the what is the safest treatment strategies. So this can be identified in the uh, healthcare. Okay. So these are all certain examples, application areas. You can see it in the healthcare. For example, surgical planning, medical device monitoring, disease progression analysis. So in that way, better treatment can be given, also reduce the healthcare cost. So next to last is the infrastructure and smart cities, uh, because this traffic management, so for example, transportation systems, or public infrastructure, this can be managed by the digital twin. Okay. So the city planners can directly use the digital twin to simulate the different scenarios and evaluate the what is the environmental impact before implementation. Okay. Like kind of they can identify the congestion points, and then they can optimize the signal timing, like this way. Okay. So many places, many things can be done, like for the development of the smart cities, by using the digital twin. That also possible. Maybe I can show you certain videos for the application. Then I will summarize last 5 minutes, maybe 5 to 10 minutes. I'll a little bit. I'll show some video. 5 minutes, maybe. So, like how it is used in the healthcare, you can see.
Sir, is there any audio in the video, sir? Audio is not coming, sir.
Hope you got the idea about like how they are using this digital twin in the healthcare. Also, little bit idea about I can show you uh, in the smart cities also how they are using it. Um, you can see that how they are uh, okay. Uh, So hopefully you got the idea about what are the smart cities, like how they're implementing this digital twin. So you can understand the virtual replica itself. You can understand the what is the actual scenario, and how you can improve the urban planning, how you can reduce the congestion. Also, how you can use the better resource utilization. All those things can be like benefits by using this digital twin. So
Sir,
now
PPT is
let's
not in
discuss
the
about a
presentation
little
mode,
bit
sir.
about what are all the
Yes, sir.
challenges and
Now it's
future trends
okay.
of digital twin. So directly I'll start with the main challenge is the data quality and availability. Okay, like because most of the cases, so So we cannot get may get inaccurate or incomplete data. So that may produce an unreliable result. So that is a main common problem. So for example, the sensor may generate a noisy signal, or sometimes it can miss the data. Sensor may get fail. In that way, the decision also will become poor. So this is the data quality is the main challenge. Second challenge is the high development and implementation cost. Again, the uh, when you are using the sensor or some kind of hardware or software expertise we need, so that will create a overall cost will be much higher, like kind of purchasing the sensor or data acquisition equipment or simulation software. These things are very costly, right? So in that way, also we have to develop the AI or skilled workforce we need to develop. So that will need some kind of high initial investment. Next is the cyber security is a nowadays issue. Data privacy also issue here, because the data theft may happen, unauthorized access may happen. It may create operational disruption, right? Like kind of we need a secure communication and data protection. So these are all certain challenges we need to overcome. Um, Next is the next challenge is the basically model accuracy and validation. Like um, here, model accuracy means what I'm saying is suppose the real time system always, mostly it is a complex system. Usually, most of the cases it is influenced by numerous variables. So engineers may frequently simplify this certain aspect of the system. They may not take the all the variables. Some of the important variables only they may take it, right? So this simplification may sometimes leads to a kind of error. Okay, so for addition to the operating condition, like kind of change over time, models must be continuously updated and recalibrated. So validation also a problem, like because it's an ongoing process rather than we can say that it is a one time activity, right? So in that way, these are also challenge one. Next is the interoperability and scalability. Scalability also a very big issue. Okay, because um, because if you're creating a digital twin for a single machine, that is relatively straightforward. But suppose if you want to do it for a entire, for example, the entire industry or entire city, then thousands of assets, significant challenges will related to the data management, computational resources, and it will create a system complexity. Okay, so that is also a very important challenge. So these are all certain challenges for implementing the digital twin. So nowadays people are going towards this future trend. Some of this AI-driven digital twins, people are trying to increase the capabilities by self-learning and intelligent decision support, adopting the new models. Okay, so in that way, the reactive system to predictive intelligence, it towards this predictive intelligence, it's moving towards uh, in the future. Okay, next is the next feature is the autonomous digital twin. So autonomous digital twin means nothing but basically uh, the digital twin should become autonomous, right? So not only detect the problem, but also it has to take the decisive or corrective action automatically. Suppose self monitoring is needed, and also automatically it has to control and it has to optimize the process. So that is also going on nowadays in that direction. Okay, third one is basically digital twin networks and human digital twins. So there are basically this suppose the organization will create a digital twin networks that may connect the all the machines, production lines, entire supply chains. So this kind of interconnected ecosystems may provide a holistic view of operations and also enable the enterprise level optimization. Okay. So another development is already I'm talking about this human digital twin. So they are trying to develop this digital representation of human organs, physiological system, and individual patients can be modeled. Okay, in that way, the doctors can predict the disease progression, and also they can evaluate the treatment. They can give the personalized healthcare solution. Okay, these are all the also some of the feature it is going ahead with that. Next important one is the industrial metaverse. Okay, industrial um, industrial metaverse means nothing but so it combines the all these digital twins with artificial intelligence, IoT, augmented reality, and virtual reality. All it combines. Okay, so in that way, the engineers can be able to enter the virtual environments. They can interact with the digital twins in real time, visualize the complex systems, and then they can evaluate the many of the operational scenarios. So also this way also this can transform the way the product are designed, manufactured, maintained, and also optimized. So in that way, digital twin will play a very central role in industry 4.0, also healthcare and future smart cities. Okay, so summary. So I will almost. So we are come to the summary of this today's session. So mostly we discuss about the what is the uh, digital twin, and then how it is the what is the historical evaluation of the digital twin and important components of the digital twin. Mainly I discuss about the digital twin development workflow. All of the components we covered. I hope you got the some basic idea about the uh, what are all the important components of the digital twin nowadays. Also some of the case studies in certain industrial areas we covered. What are the challenges and future trends also I have covered in my talk. So now we have to we have to think about this, how you can benefit your industry or research can benefit from the digital twin. You can think about it, and also what are all the application areas have in future have some highest potential. What kind of challenges may limit the digital twin adoption? These are all certain questions for the audience. I hope so. The future of engineering will be defined by intelligent systems where physical assets and digital models work together to predict, optimize, and innovate. Okay. With this, I would like to just conclude my talk today. Uh, so, if there is any queries, maybe we can go ahead with that. So also, I may show some of my area uh, that might be useful for the. Um, wait a minute, I can show some of my research area that might be useful for people, those who are wants to do some research. Maybe you can contact me. So basically, I am working in the area of manufacturing. Mainly, I'm working in the additive manufacturing of this advanced alloys. We have almost all the technology of additive manufacturing, like powder based or wire based additive manufacturing. We have it. So, different kind of material can be fabricated, 3D printed by using the uh, additive manufacturing. And also, we have some kind of conventional deformation machines, like kind of rolling machine or friction stir process machine. Okay, also for the laser surface modification technique, we have some kind of laser sharpening technique. So these are all some facilities are we have it. So also we have some kind of mechanical characterization facility and microscopes, all those facilities are available. So like if you want to see, like you can go through my website of IIT-Indore, you can book the slot. So you want to do some kind of material characterization, you can utilize those opportunity. Okay, you can go to the SIC department. There you can find the many of the equipment. Okay, so with this, I'll just conclude my talk today. Yeah, if you have any query, please you can one or two
Dear,
question I can just
dear participants,
answer it. Yeah.
do you have any questions?
Yes.
Kindly unmute and ask the question. Also post our questions in the chat box. Sir, I think no questions from the participants.
In the chart.
So we can conclude the session, sir.
Okay, so thank you. Yeah.
Sir, you have very well explained about the digital twin development workflow with the help of all the evidences and related to the industries. So thank you, sir. Thank you for accepting our invitation and spending your valuable time with us for the past 1.5 hours. So thank you, sir. Thank you very much.
Thank you, sir. Thank you very much. If there is a feature someone want to contact, maybe I can give my email ID, or you can.
Sure, sir.
Yeah, I can just writing in this my maybe.
Sir, your screen is not visible, sir.
Yeah, so I just put it in the chat box.
Okay, sir.
Yeah, so maybe you can mail me. Yeah.
Yes, sir.
Okay, sir. Thank you. Yeah.
Thank you, sir.
Yeah.
Thanks for joining, sir.
Yes.
Dear participants, we can break for the lunch. Again, today the third session will start on 2:30 p.m. So all the participants are requested to join 10 minutes earlier. Thank you. John, sir, shall we start?
Yeah, we can start. Yes.
Yes. So good afternoon to all the participants and resource person. So let me introduce the today's session speaker. So good afternoon to all. It's my privilege and pleasure to introduce our distinguished resource person, Mr. John Felix CJ, for today's session under the ISTE BNY sponsored Knowledge Enhancements Program 2026, a 6-day online faculty development program on Smart Machines 4.0, Intelligent Monitoring and Digital Twin for Data-Driven Engineering Systems, organized by Department of Mechanical Engineering, Knowledge Institute of Technology, Salem, Tamil Nadu. Mr. John Felix CJ is currently serving as the Global Innovation Head, Connectivity and Data at ZF Group, a leading global technology company driving innovation in mobility and intelligent transportation systems. With extensive experience in the domains of connectivity, data analytics, digital transformation, smart mobility, and innovation management, he has been at the forefront of developing advanced solutions that integrate data-driven intelligence with engineering systems. His work focuses on leveraging connected technologies, digital platforms, and emerging Industry 4.0 concepts to create innovative and sustainable solutions for the future. Mr. John Felix is also associated with NTU, University Singapore, reflecting his strong engagement with both industry and academia. Given his vast expertise in connectivity, intelligent systems, and digital innovation, his insights will be highly valuable to all participants, particularly in understanding the role of data, digital twins, and smart monitoring technologies in modern engineering systems. On behalf of ISTE, the organizing committee, faculty members, and dear participants, I extend a warm welcome to Mr. John Felix CJ and express our sincere gratitude for accepting our invitation to share his knowledge and experience with us. Let us all join together in welcoming our esteemed resource person, Mr. John Felix CJ. Thank you, sir. Once again, welcome you, sir. Over to you.
Thank you so much for that introduction. I really appreciate to set the context also, Mr. Mukundan. Yeah. So let me quickly share my screen. Let's start. Hope you can see my screen.
Yes, sir, it's visible.
Yes, perfect. Yeah. So very good afternoon, everyone. From my side also, a warm welcome you all to this session on this hands-on digital twin development. As Mr. Mukundan said, my name is John Felix. I'm leading a global innovation team inside ZF, commercial vehicle division. And today I would like to give share our experience of digital twin development in our organization for different use cases that we have been using and different applications of digital twin. So I sincerely hope that this information that what we share is useful for your experience and also for your future thoughts and triggering also future digital twin applications. Before I start, I also want to set some context on my background. Yeah, so I come from a very much of an AI, cloud, and data technical expertise. Given that digital twin is an amalgamation of different technologies, there are certain topics within this content which are more system oriented, or let's say more specifically. Since I know the audience here, there might be also questions around the thermodynamic models that I'm going to share. So those questions I will defer. Some of the questions I'll try to answer, and some of the questions I'll try to defer this to the an offline mode. But just to set the expectations on what I'm sharing, and also what kind of engagement that we can also have, yeah, on the specific sections of the segment that I'm sharing. Now, going into this my session here, I would like to set a short agenda. Like what I would like to talk is. First is to give a short introduction. My introduction will be a little elaborate because it will tell you a few things that needs to set the context between my experience and the audience here, and also going forward I'll also explain about the infrastructure that we depend on for developing this digital twins. And finally, go to the core session of this concept where we'd explain the concept of the digital twin, its applications, future challenges, and a few thoughts. In my opinion, a few conclusion thoughts that I also want to remark. And this is the overall, I would say, format of this session. Hopefully, this is structured well enough for your consumption. So for introduction, I would like to set few things, because digital twin is very broad topic actually, and this introduction will set to you some kind of context of who we are, like what we do, and why we are using a digital twin in our ecosystem, and that is the primary aspect, so that I can relate to the message that I'm sharing is something that is relatable to you, and also transfer as some triggers in some thoughts towards realizing this different digital twin applications. So to set the context, I would like to briefly explain where I'm working in and what domain I'm also working on. So as I mentioned in the title, I'm working for the global automotive group called ZF, and specifically I'm working in the commercial vehicle division. Within this division, we actually within the ZF is a very very well-known global tier 1 supplier for generally for different OEMs, but specifically for my division, we are a tier 1 commercial vehicle OEM supplier. For instance, in India, ZF, there is no commercial vehicle on the road without a ZF component. So we can even say that 30% of the commercial vehicle components inside an Indian commercial vehicle has a ZF component. So given that we are a very very broad, our portfolio, our product portfolio is very broad. Like you can see that we are working in different automotive subsystems, like braking subsystems, braking systems, lighting, steering solutions, suspension solutions, axles, many more. And to this talk, I also want to highlight, that we are also working on electric drive systems for heavy duty trucks.
Hello, good morning. Hello, good morning. Please
Sorry,
start your video
dear participants, someone's
and
audio is
engineering
on.
college and speak engineering.
Sir.
Yeah,
Now
thank
it's
you.
okay, sir.
Yeah, thank you for that. Yeah. So as I was saying, like we work on different portfolios, and specifically for this talk, I would be also specifically going into one specific automotive subsystem, which is this electric drive system here. And because electric drive system has a lot of its own challenges, which I'll also explain as we progress around this session. So you should know that this is the where part, like what we do part. Primarily, this theme of this session will be on 3 areas. So this, whatever the experience that we are sharing is going to be an automotive digital twin, more specifically on a commercial vehicle segment, and also more specifically, it's going to be a very India-specific topic, because I also want to share some experiences specifically that is happening in India, like with respect to the infrastructure or the evolution of digital solutions that is happening in India. So I would like to also share those experience coming from the industry. I want to share those remarks also in this. So this is the domain that I would like to share, so that it sets expectation for you. With this, I would like to also have certain fundamentals defined, because sometimes when we talk about digital twin has been, the word digital twin was there for quite some time, and the definition of a digital twin has also in some context requires clarity, because like it is, sometimes we feel that digital twin is something like a complete mirror of something that is happening in the physical world. But I would like to set my definition of what is a digital twin is. So in my opinion, or in my perspective, a digital twin is a virtual near real-time representation of a physical vehicle subsystem, more specifically like brakes, ADAS, engine, or specific subsystems. I want to emphasize here the keywords near real time. Yeah. So because normally we believe that whenever we talk about a digital twin, it's a real time reflection of something in the physical world. I would say that in our use cases, or let's say in my definition, I would say it's a near real time, where the actual reflection of the virtual world does not need to be related to time in the physical world. The second is that the virtual reflection, that what happens from the physical world to this virtual world happens through primarily data. So we believe that data is is the actual medium that reflects the physical world to the virtual world, and that is also the key driver. And finally, as I mentioned, the main message, or let's say main ambiguity that normally we have, is that a digital twin does not necessarily reflect a complete system, a complete vehicle, or a system, or even a function. Yeah? So, but it can only mirror a specific interest in a vehicle. So it need not, completely reflect everything that is there about a vehicle, that it becomes too complex to manage. And you'll also see why it's not. I would say commercially feasible to do this eventually when I highlight those challenges, what we see in the physical in these setups. So these are my definitions, so that I hope these messages can relate to you, like what I mean by the definition of a digital twin. And with these fundamentals set, I would like to then take you towards the infrastructure, that what we see with with the infrastructure that we see in India specifically for enabling digital twin ecosystems. Before I start explaining about this, I want to share a few words in India. Like India has been in many areas, given that we are a global organization, we have this exposure to different other regions. Comparing other regions, we always see that in many digital world segments, especially in automotive, India is ahead in comparing even other developed regions like Europe, or even in US. Even though those regions are catching up, we still believe that India has very well developed a very strong connectivity backbone. You'll see how and why now. And that is also the reason why there were a lot of digital applications or digital twin applications that is possible right now in that ecosystem. So for digital twins, a digital twin setup, actually, the fundamental in an automotive sector is something called the telematics ecosystem, or let's say the telematics is this digital box that sits in the vehicle that collects or logs all data from the vehicle, from different subsystems, different CAN lines, and also the other environments like location, environment, driver behavior, like a lot of other environment conditions is also captured by this telematics box. And given that data is the key attribute for any digital twin setup, this is a vital, I would say, heart of our system here actually. Yeah. So where this telematics is the key aspect that logs all the data that is coming, that is available inside the vehicle, and it streams the data to our local networks, either it's 3G, 4G, or now we are also exploring the next generation 5G networks to push this data to our cloud, and the cloud receives this and it virtualizes the systems inside the vehicle and provides insights actually. So the current telematics is not specific to digital twin. Normally, the telematics is well-defined ecosystem for fleet operations in commercial space. A lot of applications that you see in the bottom, like driver safety, fuel efficiency, these are all fleet operations specific KPIs, which are very much tracked using telematics. And telematics is very much of a core digital component fleets in India and abroad use heavily. But there are also other influences that happen and this becomes one of our key fundamental backbone infrastructure backbone to build our digital twin ecosystem. Yeah. The reason why I was very much want to highlight about India specific is because, and I also saying that India was very much ahead in the space, is because India mandated the need for a telematics box inside every commercial vehicle on 2021. So from 2021, all the commercial vehicles that are made already comes with a telematics box, collecting all the data, all the location data, all the environment data, internal vehicle data. Those data are mandated to be logged. And there is also the standardized AS 140 protocol that is mandated that needs to push data to both, interestingly, to the back end, two different servers. One is your government server. There is this, government hosted service which the commercial vehicle has to push this data into, and also the OEM owned, or let's say the third party owned cloud as well. So this becomes the fundamental backbone. That means that you already have an ecosystem that is pushing all the data that you need from the vehicle into our cloud ecosystems. And this is the reason why digital twin applications are much more easy to realize in India than abroad, because in abroad this is not mandated, but it is happening because fleets need this, and it is very much the data sources are, I would say, in private clouds. And unlike our in India, you can have access to this data in government servers as well. So this availability of data makes India a very unique scenario for us to build digital applications. Now, going on, I want to also highlight, as I mentioned, the heart of this ecosystem is your telematics. Yeah? So the modern telematics is where the entire pressure lies on, like, because it has to do many things. Even though the intelligence or the brain of the digital twin infrastructure is in the cloud, I strongly believe the heart is on the telematics here, because this is where the entire data is collected, pumped into our entire digital ecosystem. So it has to do a lot of things. Like, for instance, it has to do the basic track and trace location, environment tracking within the vehicle. Does a lot of data collection from different CAN interfaces inside the vehicle. Even does diagnostic troubleshooting in case the vehicle has certain challenges inside on the field. different sensor integrations as well, and also different subsystem integrations, like a vehicle automotive subsystem integration. So this also already gives you, a picture of how much of activities that happen in this connectivity box, actually in this telematic box, and given this intensity of data that goes through this box, there's a lot of edge computing also happens to do a first level of processing inside this telematic box, actually. So that is the that's want to highlight, like how this modern telematic hardware is also evolving. We already see that we are running out of lot of compute and memory in these boxes, and eventually the OEs are also migrating toward very high end ECUs and systems that support advanced functions eventually. So those are also evolving, but I want to highlight that these are some key building blocks in this setup. Again, I want to touch few next generation ecosystems that build or next generation technology areas that is happening at this point inside our country. Like specifically in India, like what we see is that there are a lot of regulation coming up supporting this digital infrastructure framework. One is, for example, this event data recorder, like where there is this regulation upcoming, this AIS 192, which mandates a black box kind of setup inside commercial vehicles, which logs the data. Unlike in flight, where you cannot access that black box, in here the regulation says that you can have a remote access to this black box. This means that like all the data is logged in a central store inside a vehicle, and you can have a remote access to this data store, and you can actually mine for the data from the from each of this vehicle. And similarly, there are also fundamental building blocks like cybersecurity regulation coming up, and also secure software updates is also an aspect that is enabling us to build different applications. Interestingly, like I also want to highlight this cooperative CITS, which is this cooperative intelligent transport system, and V2X, vehicle to everything communication, which talks about how instead of even just the vehicle talking to your cloud, it also talks to the vehicle and other environments around you. And this is also very much evolving in the region. So these are all I want to highlight that are data sources for us, actually, like where you are able to get data. These are all becomes a way to access data to our backend systems. I also want to touch base a specific point that is again unique to India, is this unified logistics interface platform. I'm not sure how many know this platform. This is similar to UPI in banking. India has introduced this unified logistics interface platform that integrates 33 different transport modalities in India, to a single common platform. This is something very much that we are and we are also contributing around this topic as well, like because it becomes a data store to reflect different digital twin applications for our vehicles, and to also to evaluate certain commercial vehicle aspects in this context as well. There is also other simpler use cases like this next generation GNS-based tolling. Again, this is also coming up, and also blockchain for freight and logistics is also an intelligent and secure way of managing smart logistics is also something that is happening in this industry, and all these are very much in the future of how this digital backbone in India is shaping up, again enabling towards as a different set of digital twin applications is what we anticipate. Now, coming to the core of my session here. So what I would primarily want to share is is that as you would already guessed, we are developing digital twins for different automotive subsystems that is there in our portfolio. Not all the subsystems or automotive subsystems you saw in the previous slide has a digital twin, but the ones that are more complex, more, I would say, very much technology aggressive, or let's say which requires stronger field level support, is where we identify those automotive subsystems to be identified as a potential for implementing a digital twin. And the best example is our electric drive system, In a heavy-duty truck, the electric drive system is one of the complex subsystems inside the vehicle, actually, and it's even beyond transmission. We have never seen such a complex system in the past. If comparing the level of complexities that we see integrating such a complex system, and given that the technology is new and the application of an electric drive system in a heavy-duty truck is also new, we normally we believe that a digital twin setup will actually have different uses. I'll also explain that in the next upcoming slides. So I would like to share here primarily the experience that what we had with the realization of our eDrive systems digital twin. So going into before I go into the actual digital twin concept, I would like to also highlight what are the basic fundamental building blocks of our eDrive system, so that you understand like how complex or like how vast or I would say that like like what kind of building blocks or let's say system components that what you see inside this, and how are we collecting data for this. So we have, I think most of this is something, given the current audience, I'm anticipating that you guys already know that about most of the components here in our electric drive system. You have a high voltage battery, you have a DC connector that interfaces with our electric drive system. You also have an internal DC link capacitor, which actually does an input voltage smoothing, as well as like we also have the inverter main function here, which is converting our DC voltage into a high frequency PWM interface that drives your e-motor. So at each of this block, what you have you have a lot of data sources, sensors, data sources are there actually. I also missed to mention about this, cooling loop. Like you also have water cooled function as well as oil cooled function in each of the setup. So every all this entire electromechanical system has a strong level of data that is connected, that is captured from every block what you see here. The main aspect that we also capture is how the thermodynamics works here. Like that's basically how the power and heat power transformation happens from electrical energy to this mechanical energy. And also like basically we see how much of energy is consumed, or let's say transformed at each level, from DC power to AC power, from AC power to a mechanical torque. And also like how the heat losses are generated from both inverter and as well as motor heat. All this thermal loss modeling, as well as the power modeling, as well as the individual component modeling is done. And that is a primary building block to our digital twin. So basically we want to use this flow of the thermodynamics inside our eDrive system to be captured using our digital twin concept. Now, I want to also highlight what we do actually. So this is so we have our cloud platform, like where we have used the simulation models that we have developed to build these physical components, implemented that, and we have used the data that is captured from the vehicle to feed into this simulation models. Actually, basically, it is like the simulation model is a theoretical model, and your empirical data that is coming from each component, from each of this component or from the field, models the behavior of your theoretical model inside the cloud, where that model evolves, it reflects, slowly starts to reflect the actual behavior of each of this component. And we actually have a digital twin for each of this component what you see here. For example, we have a way to also monitor how our batteries are seen, how the DC capacitor is performing, basically based on different signals and measurements that we capture from each of these stages within this. And that reflection is fed into our simulation model. We call this physics-based. It's a thermodynamics model, of course, but it is also, that model is influenced by the data. It is, again, this is a theoretical model, but it is influenced by the empirical data that is received from the physical world system, from different components. And over these model, we drive different applications like predictive maintenance. Currently, like we also very active on performance optimization, and other different applications are built over this underlying physics-based model that is influenced by the empirical data that comes from the field that drives this model. So this is our core, concept that what we have developed, like where we used the development environments what we had for developing this. We brought that into the cloud, and we started to see how that can be reflected as a way of using data from the field, and how that can be modeled to reflect how much of losses, how much of deterioration, or what is the state of health of each of this component is measured. So this is very much helping us in many things. Like I will also, before I go there, I also want to highlight this is how the data collection works. Like inside our trucks, you have different components. Like for example, we have different e-drive systems like axle systems and central drive systems that is present in our heavy duty trucks. And we have two telematics box, one from ZF and one from OE. So OEs have their own box, and because to maintain transparency of what data we capture, so this data goes to the OEM cloud, and the data from our telematic box goes to our cloud, and from there we do all the modeling, and all the other applications are built over these aspects. So this is our explains overall how our cloud ecosystem or infrastructure is set up. And primarily, I would like to touch base on 5 different applications that we already seeing that how this is creating. First is actually given that this electric drive systems are new to the road actually, so it is very new. Some of them are only in homologation at this point. Homologation means that we are trying to integrate this with the actual vehicle. And there, the primary aspect that as a tier 1 supplier, our objective was to do this performance optimization, because this is a new product on the field. We want to ensure that it fits to the requirement of how the particular vehicle was intended to be used. So the most of our primary objective for the digital twin is on performance optimization, to ensure that the product hits the road without much risks that we anticipated. Predictive maintenance is definitely the case, because it's a new component. It's a very complex component that we see, and we wanted to also have a support for field failures and also issues that we see, to give a predictive warning, because it's one of the critical components in the vehicle, and a failure of that will cause a downtime for the fleet, and it's a big commercial loss which we want to avoid, and such events will very much which will cause to lose confidence in our customers. And that's again the reason that the second priority that is on predictive maintenance as well. Thermal management is also a main point, because as I mentioned, the thermodynamics model of what is also that is happening inside our system, a digital twin setup is able to capture those aspects, and can help us to actually ensure that our system design concepts that what we had while developing this product is still valid. Like we had a lot of system and internal field tests that what we did before rolling out, but when this product hits the road, it gives you a new set of profiles, and whether those operating conditions and those thermal profiles are what we have seen during testing matches with what we see on the field is also something that is monitored. Besides that, we also do battery health monitoring. Battery is not a core component from ZF, but still it is one of a key component that we monitor, because it's one of the high value component inside the vehicle, especially on an electric truck. This is one of the very much high value component at this point. And given that the state of health of the battery is also very actively monitored to see how the battery usage is against the battery chemistry. Interestingly, there's also this 5th feature, which is this fleet operations and routing. This is not interesting for, in fact, for an OE or for a tier 1 supplier, but it is interesting for our vehicle owners who are owning this vehicles. So basically, what is OEs are right now doing is they are using this data to build revenue creating solutions for fleet operations and routing. And this has in fact created an external revenue creating stream for developing digital services around what they offer from commercial OEs to the fleet owners actually. So this is also something that is very much evolving the commercial landscape in India. So moving on, I told a lot of good things about digital twins, but I also want to highlight a lot of, I think that we still have immersive challenges in this setup. I want to highlight one big challenge that what we have. is that we call this as a data challenge, actually, because the volume of data you get from these systems is overwhelmingly large, actually. So it's just to set a context, right? So like our electric drive system with motor, all the different components generate around 800 data points. At some of the data points, it generates at 20 to 50 hertz of frequency. Now you can imagine that we have so many vehicles on the field, and ZF has a connectivity of around 2.5 lakh vehicles on the field. Even then, it's very challenging to process that immense data. So, for instance, the first bottleneck happens inside the telematics, like where the simple the number of CAN interfaces, number of subsystems, number of data points that is generated by each of the subsystems is enormous, actually, and this becomes a memory constraint for our telematics. Like we can't handle that much of data bandwidth, and also the compute to process this in a telematics box is also too high. The biggest challenge is that even though we have data, sometimes we feel that we are not able to harvest the data because of this biggest limitation that we have in the hardware on the field, actually. So and that's the reason I said in the beginning that you cannot, digital twin cannot completely reflect what is happening in the vehicle, but rather it can only take us some segments of these of your vehicle because of this primary challenge of how much data we can capture from the field. The second challenge happens, even let's say there are there are also other solutions to have a high performance node in this telematics, but even then there are other saturation points in this pipeline as well. Like the second saturation happens in network saturation. As you know, like we depend heavily on 3G and 4G networks in India. And this has a limit to how much it can transfer, and you cannot transfer the rates at what you see. This hits TBs very quickly in a day, so it becomes immensely not possible to transfer the amount of data you receive inside a vehicle. And finally, you think about instantaneous data, but also storing long-term data is also a big challenge, because even for the cloud to store long-term data is a challenge. What we anticipate, based on our experience also, we don't store beyond 3 months because it becomes too much, or I would say it is commercially doesn't make sense to store more than 3 months of data is a challenge. So again, it requires a lot of conscientious choices here to make the right decisions to choose what data points that we are choosing to log, to put in the pipeline, and also because we can also say that all data we need to store, maybe we do not know what to anticipate in the future, and that's the key word here. Like we need to be able to anticipate what we might need in the future to build this pipeline now, actually. So those are the I would say the biggest challenges what we have at this point to build our digital twin ecosystems. Again, as the challenges still outweigh the benefits, as usual. So the reason why digital twin is very much important for commercial vehicles was what I would like to highlight in this slide. One is, I would like to highlight there are some transformation happening in the automotive industry. That is, if you see, in the past, how much it took for an automotive subsystem from startup development to hit market was around 3 to 5 years. I was with Bosch for some long time, and I remember, like how long we would take to take a braking system to market. But in the recent trends, actually, recent market pushes, or let's say geopolitical dynamics, we already see that the time to market has reduced from SOD to SOPs around 6 months, and in some of these subsystems, that it puts enormous pressure on our on our development pipelines, actually, especially on automotive development pipelines, and that's something that we are not ready for. And we strongly started to believe that digital ecosystems or digital twin setups are the fundamental building blocks to avoid risk for us on the field, actually. And this is what is happening, which allows us to identify faster time to market, as well as to identify risk and field larger critical field failure much earlier on the field is what is happening. Again, the second point associated with my first point is to avoid launch failures. Actually, launch failures is the biggest, I would say, biggest concern of any tier one automotive supplier. And basically, the launch failure is an issue which happens after SOP, where you need to do a recall or even have to have a lot of consequences of a failure of a component. And this is again something that we wanted to evolve, like where after SOP we need to still have a control of our product, like where we want to see how this behaves. Even if we see a risk of a failure or a downtime of a vehicle, we need to intervene and give an early detection of that the problem. And a digital twin very much helps us in these aspects at this point. Finally, again, a lot of, as I mentioned, there is a lot of new technologies in this trends. Like as I mentioned, electric drivetrain is new. The behavior of these systems, learning about the behavior of systems, like what is optimal, is also defines our next generation strategy for our next generation products. Sometimes I also want to share, in the definition of strategy, I also want to share some experiences. When we talk about, since I come from this German organization, so I want to talk about, like we call this about German engineering. We sometimes refer this as some of the components are over-engineered to cost. Yeah, so some of the components we feel that it's over-engineered, and because of that over-engineering, it has inflated the cost of the product. And there's also the other side of the spectrum, which is what we see in China tier ones, like where we see that the cost, the actual lifetime is of those components are much less than what is the intended lifetime, and we see that it is less than ideal, design around that. So basically, we needed to have a trade-off, and basically the data-oriented solutions will, or the information that what we gather from a digital twin will rightly model our systems towards both cost and reliability and in the field, and lifetime in the field is the evolution that we see at this point. And finally, this is the biggest value add that OEs right now see, is that they are also able to generate subscription services as new digital services that drive over these frameworks, and they are able to already offer as subscription to their customers, like this new digital services, like predictive maintenance and all fleet operation based solutions. You already would have seen from different OE, from let's say Ashok Leyland or Tata. They already provide a lot of different digital applications, targeting as these are revenue creating streams for them, additional revenue creating streams for them. So with that, I would have few final thoughts. I strongly believe that the digital twin is in India specifically has already proved in many segments. A lot of achievements, like especially in automotive sector, we already seen a reduced fleet downtime. Fuel consumption is one of the biggest challenge in India, like because I missed to mention this. In the total cost of ownership of a vehicle, in normally, we say that in other regions, we say the fuel cost, the total cost in the ownership of the lifetime of a vehicle is around 20% is where the fuel cost is in other regions. In India, it comes to something around 40 or even 45%. So the fuel cost is one of the biggest costs, and every fleet operator tries to even save 1 or 2% of their fuel savings will have create a big impact. And we believe that data-oriented solutions will create that and digital twin is one of the key drivers that will enable that. Is what we anticipate. We're already seeing a strong evidence that these are already happening in our setups. The next steps, or let's say in the future, we also see that there are a lot of new other technologies, like AI is also something that is driving certain transformations in digital twin. But I'm not going to specific AI, because AI is also new in the space, but at the same time it is very disruptive, and we are very much looking towards the signals of how AI is transforming this space at this point. I also want to leave the point. The next feature is two topics. One is this. There is also this evolution of autonomous systems or fleets inside automotive, and again, how digital twin will enable that is also something that we are exploring. And more specifically, India specific is smart logistics, and that is also something that we believe that will enable new different digital twin applications, not just focusing on commercial vehicle alone, but on an entire transport industry. Transport infrastructure is what is also the evolution that we anticipate here. So with that, I would like to conclude, and I will be open to have any few questions at this point. Yeah.
Dear participants, do you have any questions? Kindly use the chat box also. Kindly unmute yourself and ask the question. I think no questions from the participants, sir.
Hello, sir. Myself, Karthik, sir.
Sir,
Yeah.
please go ahead.
Please go ahead.
Sir, the development in medical sector, what is mainly medical sector, how it is digital twins?
Karthik, I'm not from a medical background. Unfortunately, I cannot answer that question because like most of my digital twin experience is around automotive spaces at this point.
Okay, good. So, I have seen the VR and AR VR is there, sir. And what is how it will be difference between digital twin, because digital twin is virtual reality of everything, and what is how the technology changing, sir, in automotive sectors.
No, in automotive, right? Like, so it is for us. The digital twin is very straightforward. Like where we collect the data from the vehicle, from the subsystems, and we reflect that data, and that data is used to validate our original designs that we created for the automotive systems, actually. And that is how we do. So basically, we validate whether the design that what we saw during development is what we see on the field, and we use those models to also to see whether like how to assess how the actual physical composition of these components will be on the field.
Okay, sir. Thank you, sir.
Any other participant? Okay, I think no questions from the participants. So, do you want to add any more?
No, that's all I had, and thank you again for listening into this session. And I hope that the information that we shared or the experience that we shared is useful for your for your triggers and to be inspired by or to have some new digital applications around that. Yeah. And also feel free to reach out to me if you have any thoughts or questions, or also certain directions. We can also I'm open to those inputs as well. Yeah.
Thank you, sir. Oh. So one of the participants asking your email ID, sir, Virendra Singh.
Yes, I will give it here. No issues.
Better use the chat box, sir.
Yeah, I'm using it. Yes.
Yeah. Yes, sir. Okay, sir. Thank you. Sir, shall we conclude?
Yes, yeah. With that, I can conclude, and thank you again for arranging this time. Thank you again for the time. Yeah, really appreciate this, and see you soon. Yeah.
Sir, let me conclude. So once again, thank you, sir, for accepting our invitation and spend your valuable time with us for a past 1 hour. So thank you, sir. Thank you very much, sir.
Thank you.
Thank you. One more announcement to the participants. So today's all the 3 sessions are over. So we end the meeting. Again, we will meet on tomorrow morning, 9:50 a.m. Thank you.